there's a place in the universe where observation ends. Not because our telescopes aren't powerful enough, but because light itself runs out of time. Tonight on Sleepy Time Universe, we'll journey to this cosmic horizon, a boundary set by the very structure of space and time. We'll explore what creates this limit, what it reveals about the universe's history, and what might exist in the regions forever beyond our sight. Taking our time, as always, moving slowly through these ideas, giving each concept time to settle. This is an exploration of the furthest edge of the knowable universe, where causality meets its absolute boundary. Get comfortable as we begin. When we measure the universe, we find something unexpected. The region we can observe stretches roughly 93 billion light-years from one side to the other. This measurement itself contains a puzzle. The universe is only 13.8 billion years old. If light travels at a fixed speed, how can we see regions so much farther away than the age of the universe would suggest? The answer reshapes how we think about cosmic distance. Space itself has been expanding since the beginning. The galaxies and matter we see today were once much closer together. As space stretched over billions of years, objects that emitted light early in cosmic history moved farther away, even as their light traveled toward us. By the time that ancient light reaches our telescopes, the sources have receded to distances far beyond what simple multiplication of age and light speed would predict. This creates our observable universe, a sphere centered on Earth, defined not by where things are now, but by which light has had time to reach us. The boundary is not a place in space, it's a limit in time. The farthest light we detect comes from the earliest moments that photons could travel freely through the cosmos. Consider this from a different angle. Imagine standing in an enormous field at night. You hold a lamp that illuminates a circle around you. Beyond that circle lies darkness, not because nothing exists there, but because the light hasn't yet traveled far enough to reveal it. As you hold the lamp longer, the circle of visibility grows. The darkness retreats, not because it's moving away, but because light needs time to travel. Our universe works similarly. The cosmic horizon expands as the universe ages. Every moment, light from slightly more distant regions completes its journey to us. The observable universe grows larger. But this expansion of visibility is not unlimited. Other forces shape what we can ultimately see. The universe contains roughly 2 trillion galaxies within the observable region. Each galaxy holds hundreds of billions of stars. These structures cluster together in vast filaments and walls, forming a cosmic web that stretches across the visible cosmos. Between these structures lie enormous voids, regions with very few galaxies. This pattern of matter distribution emerged from tiny fluctuations in the early universe, fluctuations that quantum mechanics created when the cosmos was unimaginably small and dense. When astronomers map the distribution of galaxies, they find that the pattern appears roughly uniform at the larger scales. In every direction we look, given a large enough sample, we find similar numbers of galaxies, similar clustering patterns, similar structures. This uniformity suggests something important. The observable universe is probably not special. The regions beyond what we can see likely contain more of the same. More galaxies following similar patterns, more structures formed by the same physical laws. But here's where the concept becomes more subtle. The observable universe represents only what light has had time to show us. The actual universe, the full extent of everything that exists, could be vastly larger. It might even be infinite. We observe a patch, a sample, a window into something potentially without end. This distinction matters deeply. When we say the universe, we might mean the observable universe, the region accessible to our instruments and understanding. Or we might mean the entire universe, everything that exists regardless of whether we can detect it. These two concepts diverge dramatically in their implications. The observable universe has a finite size because light travels at a finite speed, and the universe has a finite age. These two facts combine to create an absolute limit. We cannot see beyond this boundary by building better telescopes or waiting longer, not in any practical sense. The limit is fundamental. The entire universe, meanwhile, remains unknown. It could extend far beyond what we observe. Current measurements suggest space is flat or very nearly so. In a flat universe, geometry doesn't curve back on itself. This flatness, if exact, implies the universe continues indefinitely in all directions. An infinite expanse of stars, galaxies, and space, most of which lies forever beyond our view. Some cosmologists argue the universe might be finite, but without edges, like the surface of a sphere. If you traveled in a straight line long enough, you would eventually return to your starting point, not because you encountered a boundary, but because space curves in on itself. Current observations don't support this particular geometry, but they don't rule it out completely either. Other models propose a universe that is finite and actually has edges, though no one knows what such edges would consist of or what lies beyond them. These models face theoretical difficulties. How could space simply end? What would exist at the boundary? These questions resist easy answers. For now, the evidence points toward a universe that is flat or very close to flat, which suggests it likely extends far beyond what we can observe. The observable universe becomes a bubble within something much larger, possibly infinite. We see only a fraction of what exists, and that fraction is determined by how far light has traveled since the beginning of time. This realization transforms our cosmic perspective. We're not looking at the edges of existence. We're looking at the edges of visibility. The horizon we observe is not the universe's boundary. It's the boundary of what the universe has revealed to us so far. The edge of the observable universe is often called the cosmic horizon. This term, borrowed from our everyday experience, suggests a line where Earth meets sky, a boundary we can approach, but never quite reach. The cosmic horizon shares this quality. It's always at a fixed distance from us in observational terms, but it's not a physical location we could travel to. To understand why, we need to think about horizons differently. On Earth, a horizon marks the limit of how far we can see because the planet's surface curves. Stand on a beach, and you can see perhaps 20 kilometers out to sea before the water curves below your sight line. Climb a mountain, and you can see farther because your viewing angle changes. But you never reach the horizon itself. It's not a thing or a place. It's a geometric consequence of curved surfaces and limited viewing ranges. The cosmic horizon operates on similar principles, but instead of curved planetary surfaces, we're dealing with curved spacetime and the finite speed of light. The horizon marks the limit of causal connection between us and distant regions. Events beyond the cosmic horizon cannot affect us yet, and our actions cannot influence them. No signal, no light, no information of any kind can cross this boundary within the current age of the universe. This makes the cosmic horizon fundamentally different from ordinary distance. You could imagine building a spacecraft and traveling toward a distant galaxy. Given enough time and fuel, you might reach it. But the cosmic horizon doesn't work this way. It's not defined by distance through space. It's defined by time and causality. Light from the cosmic horizon has traveled for almost the entire age of the universe to reach us. This light comes from regions that were close to us shortly after the Big Bang, but cosmic expansion has since carried those regions to enormous distances. The light itself has been stretched by this expansion, redshifted toward longer wavelengths, cooled and dimmed by the growing space through which it travels. There's something deeply strange about this. The most distant objects we can see are not the oldest. The oldest light comes from the cosmic microwave background, radiation released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form. Before that moment, the universe was opaque, filled with hot plasma that scattered light in all directions. We cannot see through this barrier to earlier times. The cosmic microwave background represents our ultimate observational limit in time, even though more distant objects exist in space. This creates two different types of horizons. The particle horizon defines the maximum distance from which light could have traveled to us, given the age and expansion history of the universe. It encompasses everything we can possibly observe. The event horizon, by contrast, defines which events we will ever be able to observe, even if we wait infinitely into the future. These two horizons differ because of cosmic expansion. The universe isn't just expanding, it's accelerating. Dark energy, a mysterious component that makes up about 70% of the universe's total energy, drives this acceleration. As space expands faster and faster, distant galaxies recede at increasing speeds. Some galaxies currently visible to us are already moving away faster than light. This doesn't violate relativity, because they're not moving through space faster than light. Space itself is expanding, carrying the galaxies with it. Their light can still reach us because they're still within our event horizon. But eventually, if cosmic acceleration continues, they will cross this boundary. Their light, already stretched to extreme wavelengths, will be redshifted into invisibility. From our perspective, they will fade from existence. This means the observable universe is not only expanding, it's also, paradoxically, shrinking in another sense. Objects we can see today will eventually become unreachable. The volume of space we can observe is growing, but the number of galaxies within our reach is decreasing. As billions of years pass, more and more galaxies will slip beyond the event horizon, their light stretched beyond detection. Future astronomers, billions of years from now, will see a lonelier universe. Fewer galaxies, more darkness, less to study and explore. They might even question whether the universe ever contained as many galaxies as our maps show. The evidence will have literally expanded away, leaving only distant memories recorded in old archives. The cosmic horizon is therefore not static. It evolves as the universe ages and expands. What we can see changes not because the horizon itself moves in space, but because time progresses and light completes new journeys. The boundary shifts according to the interplay of cosmic age, expansion rate, and the speed of light. This temporal nature of the horizon creates philosophical puzzles. If the horizon is defined by time rather than distance, then in some sense, the edge of the universe is an edge in time, not space. We're looking at boundaries of when, not where. The farthest things we observe are not distant objects in present time. They're nearby objects as they appeared in the ancient past. The distance we quote, 93 billion light years, is a calculated distance accounting for expansion. It's not a distance we could measure directly or travel across. Understanding the cosmic horizon requires accepting that the universe doesn't have edges in the familiar sense. There's no wall marking the end of space, no sign declaring beyond this point, nothing. Instead, there's a gradual fading of information, a limit to what light can show us, a boundary drawn by the fundamental physics of space, time and causality. This boundary exists everywhere in the universe, not just from our perspective. An observer in a distant galaxy would have their own cosmic horizon, centered on them, extending in all directions. Their observable universe would overlap with ours in the middle, but extend into regions we can't see. Meanwhile, they would be unable to observe regions visible to us in the opposite direction. In this sense, the cosmos is filled with overlapping bubbles of observability. Each point in space serves as the center of its own observable sphere. No location is privileged. Every observer, wherever they exist in the universe, finds themselves at the apparent center of their own cosmic horizon. This is not coincidence or cosmic preference, it's geometry. It's the structure of space-time combined with the finite speed of light and the age of the universe. The horizon exists because information takes time to travel, and the universe hasn't existed forever. To understand what might exist beyond the cosmic horizon, we need to explore how the universe began and evolved. The leading framework, cosmic inflation, suggests the universe underwent a period of extraordinarily rapid expansion in its first fraction of a second. During this inflationary epoch, space expanded faster than light could cross it. A region smaller than a single atom swelled to cosmic scales in an incomprehensibly brief instant. Inflation solves several puzzles about the early universe. It explains why distant regions of space have nearly identical temperatures, despite being too far apart to have ever exchanged light or heat. It explains why space appears flat rather than curved. It explains the pattern of small density variations that eventually became galaxies and clusters. These features emerge naturally from quantum fluctuations stretched to cosmic scales during the inflationary burst. But inflation creates new mysteries. If inflation happened once, did it stop everywhere simultaneously? Many models suggest it didn't. In these eternal inflation scenarios, most of space continues inflating forever. Only in rare pockets does inflation end, allowing normal expansion to take over and matter to form. Our observable universe would be one such pocket, a bubble where inflation stopped and stars and galaxies could eventually emerge. If eternal inflation is correct, the universe is far larger than the region we observe. Vastly, perhaps infinitely larger. Beyond our cosmic horizon lie other bubbles, other regions where inflation ended at different times and under different conditions. Some might resemble our universe. Others might have different physical properties, different values for fundamental constants, different laws governing how particles and forces behave. This transforms the cosmic horizon from merely an observational limit into something more profound. It becomes a boundary separating our universe, our pocket of reality, from an endless expanse of other pockets. Each bubble remains causally isolated from the others. No light, no signal, no information can cross from one bubble to another because they're separated by regions of space that are still inflating, expanding faster than light can traverse them. In this framework, the word universe becomes ambiguous. We might use it to mean our observable universe, the region we can study. We might mean our entire bubble, the region where inflation ended and matter formed, which extends far beyond what we can see. Or we might mean the multiverse, the full collection of all bubbles across all of space, most of which remain forever beyond our reach. The concept of an infinite universe emerges naturally from these models. If space is flat and inflation continues eternally in most regions, then space has no edge and no center. It simply extends indefinitely in all directions. Within this endless expanse, countless bubbles form, each one a potentially vast region of normal space embedded in the inflating bulk. Some cosmologists argue that if the universe is truly infinite, then probability becomes strange and interesting. In an infinite universe, every possible configuration of matter would occur somewhere. Not just once, but infinitely many times. There would be regions unimaginably distant where matter arranged itself into galaxies identical to ours, planets identical to Earth, beings identical to each one of us, living identical lives. This seems paradoxical, but it follows from the mathematics of infinity. If every possible arrangement occurs, and you have infinite space to work with, then every arrangement occurs infinitely often. The observable universe we inhabit, with all its specific features and details, would be repeated endlessly throughout the infinite expanse. Most cosmologists remain cautious about such claims. The argument relies on assumptions about probability and randomness that might not hold. It assumes matter arranges itself randomly across infinite space, which inflation doesn't necessarily guarantee. Even if the universe is infinite, it might contain patterns or structures at scales far beyond what we can observe, making naive probability arguments unreliable. Still, the possibility lingers. If the universe is infinite and matter is distributed with some degree of randomness, then distant regions might mirror our own, not because of any causal connection or cosmic conspiracy, but simply because infinity permits all possibilities. This raises questions about uniqueness and identity. If countless versions of Earth exist, scattered across an infinite cosmos, each hosting identical histories and people, what does it mean to be an individual? Are those distant copies truly separate beings? Or are they somehow the same person existing in multiple locations? Philosophy struggles with such questions, and physics offers no clear answers. Setting aside these puzzles, eternal inflation suggests that the observable universe represents an infinitesimally small fraction of all that exists. The cosmic horizon doesn't mark the edge of space. It marks the edge of a bubble within an endless ocean of other bubbles, most of which we can never observe or study. Even within our own bubble, far beyond the cosmic horizon, space likely continues for enormous distances. The observable universe, 93 billion light-years across, might be a tiny patch within a bubble billions or trillions of times larger. Light from these regions hasn't had time to reach us yet. It never will, because cosmic expansion accelerates, stretching space faster than light can close the gap. So what exists in these unreachable regions? Probably more galaxies, more stars, more planets. The laws of physics should be the same because they're part of the same bubble, the same region where inflation ended. Matter would have formed from the same quantum fluctuations, evolved under the same gravity and thermodynamics, assembled into familiar structures like stars and galaxies. But we can't be certain. We can only extrapolate from what we observe nearby. The universe might contain large-scale patterns or features that only become apparent across distances vastly exceeding the observable universe. There might be gradients in fundamental constants, subtle variations in physical laws that change over cosmic distances. We have no way to know. Some theorists propose that different bubbles within the eternal inflation landscape might have genuinely different physics. The fundamental constants we measure, things like the strength of gravity or the mass of electrons, might not be fundamental at all. They might be environmental variables, properties that took on different random values in different bubbles when inflation ended. If true, this would mean our universe's physics is somewhat arbitrary. Other bubbles might have stronger or weaker forces, heavier or lighter particles, more or fewer dimensions. Most combinations would produce sterile universes where matter can't form or stars can't ignite. The parameters we observe might be selected by a kind of cosmic coincidence. We exist in a bubble where the physics happens to allow for complexity, structure, and ultimately, observers. This line of thinking leads to the anthropic principle, the idea that we observe the universe we do partly because we exist. Only universes with physics compatible with life can be observed by living beings. The vast majority of bubbles might be empty, hostile, or simply unable to support the kind of chemistry and structure necessary for consciousness to emerge. Whether this explanation satisfies depends on philosophical taste. Some find it elegant, a way to explain why fundamental constants have the seemingly fine-tuned values we measure. Others find it unsatisfying, more of an excuse than an explanation. It replaces "why is gravity this strength?" with "because in most bubbles it's different, and we couldn't exist there." The question shifts, but perhaps doesn't truly resolve. Regardless of interpretation, eternal inflation paints a picture of vast, perhaps infinite, space extending beyond the cosmic horizon. Our observable universe becomes a small, local sample of something enormously larger. The horizon isn't the edge of existence. It's merely the edge of what light has revealed to us so far. Understanding what lies beyond the cosmic horizon also requires considering the shape of space itself. When we think about distance, we usually imagine flat, Euclidean geometry. Draw a triangle, and its angles sum to 180 degrees. Draw a circle, and its circumference equals pi times its diameter. These familiar rules govern the space we experience in everyday life. But space on cosmic scales might not be flat. General relativity allows for curved space-time, where geometry differs from our intuitive expectations. A triangle drawn across curved space might have angles summing to more or less than 180 degrees. Parallel lines might converge or diverge. The large-scale shape of space affects what exists beyond the horizon and whether the universe is finite or infinite. Astronomers measure the curvature of space by examining the cosmic microwave background. The patterns of hot and cold spots in this ancient radiation encode information about the geometry of the universe. If space is flat, these patterns have certain sizes and distributions. If space is curved, the patterns differ in predictable ways. Current measurements indicate the universe is flat within a small margin of error. The best data suggests curvature is zero or extremely close to zero. This finding supports inflation theory, which predicts that rapid expansion should stretch any initial curvature until space becomes virtually flat. It's like inflating a balloon to enormous size. The surface might be curved locally, but any small patch appears flat because the radius of curvature becomes so large. If space is exactly flat, the universe is likely infinite. There's no curvature to cause space to close back on itself, so it extends forever in all directions. The observable universe becomes an infinitesimal point within an endless expanse. Beyond the cosmic horizon lies more space, more matter, more structure, continuing without bound. But measurements aren't perfect. There's a small possibility space has positive curvature, like the surface of a sphere. In such a universe, space curves back on itself. Travel in a straight line long enough, and you'd return to your starting point, not because you hit a wall and turned around, but because space itself loops. A positively curved universe would be finite but boundless. It has no edges, yet it contains a limited volume of space. This seems paradoxical at first. How can something be finite without having boundaries? The surface of a sphere provides the answer. It's finite in area, yet you can travel across it endlessly without ever finding an edge or falling off. If our universe has positive curvature, The total volume of space is enormous, but not infinite. The cosmic horizon might encompass a significant fraction of all that exists. Travel far enough beyond the horizon, in principle, and you'd eventually circle back toward the observable region from the opposite direction. Light emitted billions of years ago might have circumnavigated the universe multiple times, creating strange optical effects where we observe the same galaxies in multiple directions. Current observations show no evidence for this. The universe appears too large and too flat for such effects to be detectable. If space is curved, the radius of curvature exceeds the observable universe by a substantial margin. For practical purposes, space behaves as if it's infinite. There's also theoretical possibility of negative curvature, like the surface of a saddle. In negatively curved space, geometry works differently again. Parallel lines diverge, triangles have angles summing to less than 180 degrees, and space extends infinitely. Negative curvature doesn't close space back on itself. It allows for infinite volume, like flat space, but with different geometric properties. Observations slightly favor flat space over negatively curved space, but the distinction is subtle and depends on precise measurements. For our purposes, both scenarios lead to similar conclusions. Beyond the cosmic horizon lies vast, possibly infinite, space filled with matter and structure. The shape of space also affects the fate of the universe. In a flat or negatively curved universe with dark energy, expansion accelerates forever. Galaxies drift apart, stars exhaust their fuel, and eventually the cosmos fades into cold darkness. This ultimate fate, called heat death or the Big Freeze, lies trillions of years in the future, but it represents the likely endpoint of cosmic evolution. In a positively curved universe, the outcome depends on the balance between curvature and dark energy. If curvature dominates, expansion might eventually halt and reverse, leading to a big crunch where the universe collapses back into a hot, dense state. Current measurements suggest dark energy dominates, making a big crunch unlikely. But if our understanding of dark energy is incomplete, other possibilities remain open. These considerations affect how we think about the cosmic horizon. If the universe is finite and curved, the horizon might eventually encompass most or all of existence. In the distant future, if expansion decelerates or reverses, we might observe regions currently beyond our reach. The horizon would shift, revealing new portions of the cosmos. But if the universe is flat and accelerating, the opposite occurs. The event horizon shrinks as acceleration continues. More galaxies slip beyond reach, their light stretched into invisibility. The observable universe grows in volume but contains fewer structures. The horizon becomes an ever-tightening boundary, cutting us off from an increasingly large fraction of the cosmos. The geometry of space thus determines not just the size of the universe, but the nature of cosmic boundaries. Flat space suggests an infinite expanse beyond the horizon, forever unreachable, but potentially similar to what we observe. Curved space might limit the total volume, but create strange topologies where distant regions connect in unexpected ways. Current evidence favors flat space and an infinite universe. This means the cosmic horizon doesn't mark the edge of existence. It marks the edge of causality and observation within an endless expanse. What lies beyond probably resembles what lies within. More galaxies, more stars, more planets, governed by the same physical laws, following the same patterns of structure and evolution. But probably isn't certainly. The universe might surprise us. There might be features at scales larger than the observable universe that change the picture entirely. Without access to these regions, we can only speculate and extrapolate. The cosmic horizon remains a fundamental barrier to knowledge, a limit imposed by the nature of space, time, and light. When we attempt to observe the cosmic horizon, we're really observing the past. The farthest we can see isn't distant space, but ancient time. The oldest light detectable comes from the cosmic microwave background, radiation that has traveled across the universe for over 13 billion years. This light carries information about the early universe, frozen in patterns that reveal the conditions shortly after the Big Bang. The cosmic microwave background formed when the universe was about 380,000 years old. Before this moment, the universe was too hot and dense for atoms to hold together. Electrons and protons existed separately in a plasma that scattered light in all directions. The universe was opaque, filled with glowing fog that prevented photons from traveling far. As the universe expanded and cooled, electrons and protons combined to form neutral atoms. This process, called recombination, suddenly made the universe transparent. Light could travel freely across space for the first time. The photons released during recombination have been traveling ever since, stretched by cosmic expansion from visible light into microwaves. We detect this ancient radiation as a faint glow coming from every direction in the sky. The temperature is cold, just a few degrees above absolute zero, but the signal is unmistakable. Instruments have mapped the cosmic microwave background with extraordinary precision, revealing tiny variations in temperature across different regions of the sky. These temperature variations, typically just a few millionths of a degree, represent the seeds of all cosmic structure. Slightly denser regions appear slightly warmer. Slightly less dense regions appear slightly cooler. These density differences, created by quantum fluctuations in the first moments after the Big Bang, eventually grew under gravity to become galaxies, clusters, and the cosmic web we observe today. The cosmic microwave background provides our deepest view into the past. It shows the universe as it was before stars formed, before galaxies assembled, before any of the complex structures we observe came into being. It's a snapshot of cosmic infancy, a record of the conditions that set the stage for everything that followed. The patterns in the cosmic microwave background also reveal information about the size and shape of the universe. The size of the hot and cold spots depends on the geometry of space. In flat space, the spots have one characteristic size. In curved space, they appear larger or smaller depending on the direction of curvature. Measurements show the spots have exactly the size predicted for flat space, within measurement error. This is one of the key pieces of evidence supporting the conclusion that space is flat or very nearly so. It suggests the universe is likely infinite, extending far beyond the cosmic horizon in all directions. The patterns we observe in the cosmic microwave background probably repeat across vast distances, creating similar structures in regions we can never observe. But the cosmic microwave background also represents a barrier. We cannot see through it to earlier times. The universe was opaque before recombination. Any light from earlier epochs scattered repeatedly and lost all information about its source. The cosmic microwave background is the oldest light we can detect, the ultimate horizon in time. Scientists have searched for indirect ways to probe beyond this barrier. Gravitational waves, ripples in space-time itself, might carry information from earlier epochs. Unlike light, gravitational waves don't scatter off matter. They should propagate freely even through the opaque early universe. Detecting primordial gravitational waves from the first moments after the Big Bang remains a major goal of observational cosmology. Neutrinos, ghostly particles that barely interact with matter, might also carry information from very early times. A cosmic neutrino background should exist, analogous to the cosmic microwave background, but even older. Neutrinos decoupled from matter about 1 second after the Big Bang, much earlier than photons. Detecting this neutrino background would provide a view into an even earlier epoch. These potential observations would push the horizon back slightly, revealing conditions in the first seconds or fractions of a second after the Big Bang. But they wouldn't remove the horizon entirely. There will always be a limit to what we can observe, set by the age of the universe and the finite speed at which information can travel. The cosmic microwave background itself is moving farther away as the universe expands. The matter that emitted this radiation is now about 46 billion light-years distant, carried to that distance by cosmic expansion. In billions of years, this distance will grow larger. The cosmic microwave background will be redshifted to even longer wavelengths, becoming fainter and harder to detect. Eventually, trillions of years in the future, the cosmic microwave background might fade beyond detection. Future astronomers would lose access to this crucial evidence about the early universe. They would see only the nearby galaxies that hadn't yet slipped beyond the event horizon. Their observable universe would contain far less information about cosmic origins than ours does. This demonstrates how the cosmic horizon evolves. What we can observe depends not just on the age of the universe, but on its expansion history and future evolution. As dark energy drives accelerating expansion, some information becomes permanently unreachable. The horizon shifts, and with it, the limits of what any observer can possibly know about the cosmos. The cosmic microwave background reminds us that the universe has a history. It wasn't always as it is now. The structures we observe formed gradually over billions of years, evolving from the tiny seeds visible in that ancient radiation. The galaxies, stars and planets emerged from simpler initial conditions shaped by gravity, nuclear physics, and thermodynamics. This historical perspective changes how we think about the cosmic horizon. We're not just observing distant space. We're observing the entire history of the universe, layer by layer, with the farthest objects showing the youngest epochs. The cosmic horizon represents the beginning of observable time. Beyond it lies not more distance, but more time, epochs so early that light hasn't had time to reach us yet. But those epochs may never become observable. As expansion accelerates, the event horizon contracts. Some regions of space that are currently just beyond our view will remain beyond it forever. Their light, emitted billions of years ago, races toward us, but never closes the gap because space expands faster than light can traverse it. The cosmic horizon becomes a permanent barrier, separating what can be known from what must remain forever mysterious. The cosmic horizon is not static. Its behavior depends on the expansion rate of the universe, and that expansion rate is changing. For billions of years, gravity slowly decelerated cosmic expansion. Then, about 5 billion years ago, something strange happened. Expansion began accelerating. The universe started growing faster and faster, driven by a mysterious component called dark energy. Dark energy is one of the deepest mysteries in modern physics. It makes up roughly 70% of the total energy content of the universe, yet we understand almost nothing about its nature. We know it exists because we observe its effects. Distant supernovae appear fainter than they should, indicating the universe is expanding faster than earlier models predicted. Galaxy clusters show patterns consistent with accelerated expansion. The cosmic microwave background contains subtle features that point to dark energy's influence. But knowing that dark energy exists doesn't explain what it is. The simplest possibility is that it represents the energy of empty space itself, a property of the vacuum. Quantum field theory predicts that even empty space should have a small amount of energy. This vacuum energy would act like dark energy, causing space to expand. The problem is that calculations predict vacuum energy should be either zero or enormously large, not the small but significant value we observe. This discrepancy, called the cosmological constant problem, represents one of the greatest challenges in theoretical physics. The energy of empty space should be either completely negligible or so enormous that it would have ripped the universe apart instantly. Instead, it's small enough to be irrelevant for most of cosmic history, but large enough to dominate the universe's energy budget today. Some theories propose that dark energy isn't constant, but changes over time. In these models, dark energy might have been weaker in the past and could become stronger or weaker in the future. This dynamic dark energy goes by various names, quintessence being the most common. It behaves differently than a cosmological constant and might interact with matter and radiation in subtle ways. If dark energy is changing, the fate of the universe becomes less certain. The expansion might continue accelerating forever, leading to a cold, dark future where galaxies drift apart and stars exhaust their fuel. Or dark energy might weaken, allowing gravity to slow expansion, perhaps even leading to eventual collapse. Or dark energy might strengthen dramatically, tearing apart galaxies, stars, planets, and eventually atoms themselves in a big rip. Current observations favor a cosmological constant, unchanging dark energy that maintains consistent strength over time. If this is correct, the universe will expand forever, with acceleration continuing indefinitely. The cosmic horizon will evolve in predictable ways, gradually cutting us off from more and more of the cosmos. This accelerating expansion affects what lies beyond the cosmic horizon. Some of those distant regions are receding from us faster than light, not because they're moving through space faster than light, which would violate relativity, but because space itself is expanding. The galaxies aren't racing through space. Space is carrying them along as it grows. This creates a counterintuitive situation. Light from these distant galaxies is traveling toward us at the speed of light, but the space between us and them is expanding faster than light can close the gap. The light makes progress in local terms, crossing billions of light years of space, but globally, the distance to the source keeps increasing. The light never gets closer to us in absolute terms. Eventually, if acceleration continues, this light will be stretched to such long wavelengths that it becomes undetectable. The photons lose energy as space expands, their wavelength growing longer. They fade into the infrared, then the microwave, then radio waves with wavelengths spanning light years. At some point, the energy per photon becomes so small that no detector could possibly register it. This means objects currently just beyond the cosmic horizon will eventually fade from observability. They're not moving away from us in any ordinary sense. They're being carried by expanding space into regions from which no signal can ever reach us. The event horizon represents this ultimate boundary. Beyond the event horizon lie regions of space that are fundamentally disconnected from us. No information from those regions can ever arrive here, no matter how long we wait. The particle horizon, by contrast, represents the current boundary. It marks the distance light could have traveled since the Big Bang given the universe's expansion history. Objects beyond the particle horizon are currently unobservable because their light hasn't reached us yet. But in principle, if we wait long enough, light from slightly beyond the current particle horizon will eventually arrive. The particle horizon grows as the universe ages, but the event horizon shrinks. As acceleration continues, regions of space that are currently observable will eventually slip beyond the event horizon. Their light will be redshifted beyond detection. From our perspective, they will fade from existence. The observable universe will contain fewer and fewer galaxies as billions of years pass. This creates a strange and melancholy picture of the far future. Intelligent observers arising trillions of years from now would see a much emptier universe. Only the galaxies gravitationally bound into their local group would remain visible. Everything else would have receded beyond the event horizon. These future observers might conclude they live in a small, isolated universe, unaware that they're surrounded by countless galaxies that have simply become unobservable. They might even doubt the Big Bang theory. The cosmic microwave background would have faded beyond detection by then. The evidence for cosmic expansion would be subtle and difficult to measure. Without the historical context we have, future cosmologists might struggle to understand the universe's origin and evolution. Key evidence will have literally expanded away, lost to the accelerating growth of space. This highlights the privileged moment we occupy in cosmic history. We live at a time when the universe is old enough for stars and galaxies to have formed, but young enough that we can still observe the cosmic microwave background and see distant galaxies from various epochs. We can piece together the universe's history because we have access to evidence spanning billions of years. Future observers will not be so fortunate. Dark energy thus shapes the cosmic horizon in profound ways. It determines how the horizon evolves, which regions remain observable, and what future observers will be able to see and understand. The mysterious force accelerating expansion also controls the boundaries of knowledge itself, deciding which questions can be answered and which must remain forever beyond reach. Understanding dark energy remains one of the central challenges in cosmology. Solving it would not only explain the universe's expansion, but also clarify what lies beyond the cosmic horizon. If dark energy is truly constant, the future is predictable. The universe will expand forever, and more galaxies will slip beyond reach. If dark energy changes or interacts with matter in unexpected ways, the picture becomes more complex and interesting. For now, we watch the horizon evolve, measuring its properties, tracking which galaxies are receding most rapidly, and trying to predict the long-term fate of observable cosmos. The cosmic horizon is not fixed. It breathes with the expansion of space, growing in some senses and shrinking in others, always remaining just beyond our grasp. When we consider what might exist beyond the cosmic horizon, the most radical possibility is that our observable universe represents just one small region within a much vaster structure. This is the realm of multiverse theories, frameworks suggesting that what we call the universe is actually one bubble in an infinite foam of universes. Several different types of multiverse have been proposed, each arising from different physical theories. The distinctions matter because they make different predictions about what lies beyond our horizon and whether those regions are fundamentally similar to or different from our own. The simplest multiverse concept emerges directly from cosmic inflation. If inflation is eternal, most of space continues inflating forever. Only in rare pockets does inflation end, allowing normal expansion and matter formation to proceed. Our observable universe is one such pocket, the region where inflation ended and stars could form. Beyond our cosmic horizon, space might still be inflating in some regions. These inflating regions separate different pockets from each other, ensuring they remain causally disconnected. No light or signal can cross from one pocket to another because the space between them expands faster than light can travel. Each pocket within this eternal inflation scenario is called a bubble universe. These bubbles can be enormously large, far exceeding the size of our observable universe. The portion we see might be a tiny fraction of our own bubble, with vast regions beyond our horizon, but still part of the same pocket where inflation ended. Other bubbles exist elsewhere in the inflating expanse. They formed when inflation ended in those regions, perhaps billions of years before or after inflation ended in our region. Each bubble has its own history, its own galaxies and stars, its own evolution. The bubbles don't interact. They're islands of normal space embedded in an ocean of eternally inflating territory. This picture makes the cosmic horizon even more significant. It separates not just our observable universe from unobservable regions, but potentially our entire bubble from fundamentally disconnected bubbles. The horizon marks a boundary beyond which the very concept of space and time might work differently. A more speculative multiverse concept arises from string theory and the landscape problem. String theory suggests that fundamental constants, like the strength of gravity or the mass of the electron, aren't truly fundamental. They're environmental variables that can take different values in different regions of space. The landscape of string theory contains an enormous number of possible configurations, each corresponding to different values for physical constants. Some estimates suggest there might be 10 to the power of 500 different possible sets of laws of physics. This is an unimaginably large number, far exceeding the number of atoms in the observable universe. If eternal inflation occurs within this landscape, different bubbles might have different physics. When inflation ends in a particular region, the constants and forces settle into one of the many possible configurations. Our bubble happens to have the physics we observe, but other bubbles might have stronger gravity, weaker electromagnetism, more dimensions of space, or entirely different particle physics. Most configurations would be sterile, unable to form atoms or stars or any complex structure. The parameters we observe appear fine-tuned for life. Change any of several constants by even a small amount and stars can't form, or chemistry doesn't work, or the universe collapses before galaxies can assemble. In a landscape multiverse, this fine-tuning becomes less mysterious. If countless bubbles exist with different physics, we naturally find ourselves in one where the physics permits life. All the other bubbles exist, but no observers arise there to wonder about cosmic parameters. This is the anthropic principle applied to the multiverse. We observe our universe's physics not because it's special, but because we can only exist in bubbles where the physics happens to work. Whether this explanation satisfies depends on philosophical taste. It trades one mystery for another. Instead of asking why our universe has the parameters it does, we ask why the multiverse has a landscape of possibilities and why eternal inflation explores that landscape. The question doesn't disappear. It shifts to a different level. Another type of multiverse emerges from quantum mechanics. The many worlds interpretation suggests that every quantum measurement creates a branching of reality. The universe splits into multiple copies, each representing a different possible outcome. Over time, these branches multiply exponentially, creating an ever-growing tree of parallel realities. In this quantum multiverse, other versions of you exist in other branches, experiencing different outcomes of quantum events. Most branches are very similar to ours, differing only in tiny quantum details. Some branches diverge more dramatically if key quantum events had different outcomes early in cosmic history. This quantum multiverse is different from the eternal inflation multiverse. The branches don't occupy different regions of space. They're more like different layers of reality, existing in the same space but not interacting. You can't travel from one branch to another. They're separated not by distance, but by quantum divergence. Some theorists suggest combining these ideas. Perhaps eternal inflation occurs in a landscape of string theory, while quantum mechanics causes branching within each bubble. The result would be a staggeringly complex structure where countless bubbles exist, each containing countless quantum branches, creating a multiverse of multiverses. These speculative ideas push far beyond what can currently be tested. We have no way to observe other bubbles or quantum branches. The cosmic horizon prevents us from detecting most of eternal inflation's consequences. Quantum branching, if it occurs, happens in ways that don't allow communication between branches. The theories make testable predictions within our observable universe, but their claims about what lies beyond remain speculative. Still, the multiverse concept offers a framework for thinking about the cosmic horizon. It suggests that what lies beyond might be genuinely different from what we observe, not just more of the same galaxies and stars. Other bubbles might have alien physics. Other quantum branches might have experienced different histories. The horizon doesn't just hide more space. It might hide genuinely new types of existence. Whether any of this is true remains unknown. The multiverse might be real, with countless bubbles and branches extending beyond our horizon. Or the universe might be simpler, containing only one bubble with uniform physics throughout, extending perhaps infinitely in all directions. Current observations don't decisively distinguish these possibilities. What we can say is that the cosmic horizon limits what we can ever know about such questions. Even if other bubbles exist, we can't observe them. Even if quantum branching occurs, we can't detect other branches. The theories remain forever beyond direct experimental confirmation. We can test their predictions within our observable universe, but we can't verify their claims about what lies beyond the horizon. This epistemological limitation frustrates some scientists and philosophers. Science traditionally deals with testable predictions. If a theory makes claims that can never be verified or falsified, even in principle, is it really science, or has it crossed into metaphysics and philosophy? These questions have no clear answers. Multiverse theories arise from well-established physics, like inflation and quantum mechanics. They follow logically from principles we've tested extensively within our observable universe. But their predictions about unobservable regions push against the traditional boundaries of scientific method. For now, we study what we can observe and build theories that explain those observations. If those theories predict multiverse structures beyond the cosmic horizon, we take note of the prediction while acknowledging the limits of verification. The horizon remains a boundary not just for light and information, but for knowledge itself. The cosmic horizon raises profound philosophical questions. If regions of space exist that are forever unobservable, can we meaningfully say they're real? Does existence require observability, or do things exist independently of whether we can detect them? These questions touch on deep issues in philosophy of science. Realism, the view that reality exists independently of observation, suggests that regions beyond the cosmic horizon are just as real as the space around us. The fact that we can't see them doesn't make them any less existent. They're simply beyond the causal boundaries that limit what we can observe. Instrumentalism, by contrast, focuses on observational consequences. From this perspective, claims about unobservable regions are only meaningful insofar as they affect observable predictions. If a theory predicts structures beyond the horizon, but makes no testable claims about what we can see. Instrumentalism questions whether those predictions have scientific content. Most physicists lean toward realism in practice. The laws of physics we've tested locally should continue to apply in regions we can't observe. Gravity doesn't stop working beyond the cosmic horizon. Atoms don't change their properties. The universe doesn't care about the limits of human observation. This realist stance suggests that vast expanses of space, galaxies, stars, and potentially life exist beyond the cosmic horizon, following the same patterns and laws we observe nearby. We can't verify this directly, but it follows from the uniformity and universality of physical law. But some physicists argue that the cosmic horizon might have deeper significance. If information truly cannot cross the horizon, then in what sense do regions beyond it exist for us? They can never affect us. We can never affect them. No exchange of energy, matter, or information is possible. They're completely disconnected from our causal patch of the universe. This leads to a version of the holographic's principle, the idea that all the information about a region of space might be encoded on its boundary. If this principle applies to the cosmic horizon, then perhaps the observable universe contains all the information that exists, in some sense. The regions beyond the horizon might not add new information. They might be, in some strange way, redundant or less fundamentally real than they appear. These ideas remain highly speculative. The holographic principle is well established in certain contexts, particularly black hole physics. Whether it applies to cosmic horizons in similar ways remains an open question. But the possibility suggests that the horizon might be more than just an observational limit. It might represent a fundamental boundary in the structure of reality itself. Another philosophical puzzle concerns probability and infinity. If the universe is infinite, as current evidence suggests, then every possible configuration of matter occurs somewhere. Not just once, but infinitely many times. This includes exact copies of our solar system, our planet, even ourselves. Some philosophers find this conclusion troubling. If infinitely many copies of you exist throughout the infinite universe, what does personal identity mean? Are those distant copies truly separate beings? Or are they somehow the same person? If they make different choices due to quantum randomness or different local conditions, which version is really you? These questions mix physics with metaphysics. Physics tells us that in an infinite universe with some degree of randomness, recurrence is mathematically inevitable. Philosophy asks what this means for concepts like identity, responsibility, and meaning. There are no clear answers. The cosmic horizon also raises questions about the limits of scientific knowledge. Science progresses by testing predictions against observations. Theories that make testable predictions and survive experimental challenges gain confidence. Theories that make no testable predictions or fail experimental tests are discarded or modified. But what about theories that make predictions about regions beyond the cosmic horizon? These predictions can never be directly tested. We can check whether the theories correctly predict what we observe within the horizon. If they do, that provides some confidence. But we can't verify their claims about what lies beyond. This creates an epistemological boundary. There are questions we can formulate clearly, but can never answer through observation. What exactly exists beyond the cosmic horizon? How large is the entire universe? Do other bubbles exist with different physics? These questions might have definite answers, but those answers remain forever beyond our reach. Some philosophers argue this represents a fundamental limit to human knowledge. We can speculate, theorize, and extrapolate, but we can never know with certainty What lies beyond the boundary of observation? The cosmic horizon marks the edge not just of the observable universe, but of the knowable universe. Others argue that this limit is practical rather than fundamental. In principle, the laws of physics should allow us to infer what lies beyond the horizon based on what we observe within it. If the universe is uniform and follows consistent laws, then the unobservable regions probably resemble the observable ones. We can't verify this directly, but we can have justified confidence based on the uniformity we do observe. This debate connects to broader questions about scientific realism and the nature of explanation. Do theories need to be testable to be scientific? Or is it enough that they follow logically from well-tested principles and provide coherent explanations for what we observe? Most working scientists don't worry too much about these philosophical questions. They develop theories, make predictions, test them against observations, and refine their understanding. If theories suggest structures beyond the cosmic horizon, that's noted as an interesting consequence. But the focus remains on testable predictions and observable phenomena. Still, the cosmic horizon reminds us that science has limits, not limits of human ingenuity or technological capability, but limits imposed by the structure of reality itself. Some questions might have answers we can never access. Some regions of space might exist that we can never observe. Some aspects of the universe might forever remain beyond the reach of scientific investigation. This realization is both humbling and liberating. Humbling because it shows that however much we learn, there will always be more that remains unknown. The cosmic horizon ensures that our knowledge can never be complete. Liberating because it shows that reality is larger and richer than any human mind can fully grasp. The universe contains mysteries that exceed our ability to solve them, phenomena that transcend our capacity to observe them. The cosmic horizon stands as a permanent monument to the unknown, a boundary that will never be crossed, a limit that will never be overcome. Beyond it lies everything we cannot see, cannot measure, cannot know. And yet, through reason and imagination, through physics and mathematics, we can at least conceive of what might be there. We can build models, make predictions, and explore the possibilities. Even if we can never verify them directly, we can satisfy ourselves that we understand, as well as anyone can, the nature of the boundary itself. The cosmic horizon creates a kind of loneliness. As the universe expands and acceleration continues, we become increasingly isolated from distant regions. Galaxies that we can observe today will eventually recede beyond the event horizon. Their light will be redshifted beyond detection. From our perspective, they will fade into nothingness. This process is already underway. The most distant galaxies we observe are receding faster than the speed of light, due to the expansion of space. Their light reaches us only because they're still within our event horizon. But that window is closing. In billions of years, many of these galaxies will slip beyond the boundary, becoming forever unobservable. Future astronomers, billions of years from now, will see a lonelier cosmos. Only the galaxies gravitationally bound to our local group will remain visible. The Milky Way, Andromeda, and a few dozen smaller galaxies will form an isolated island in the darkness. Beyond this small cluster, the universe will appear empty. These future observers might conclude that the universe consists only of their local group. They would have no evidence for the billions of other galaxies we can see. The cosmic microwave background would have faded beyond detection. The expansion of space would be too slow to measure within their local group. They would lack the key evidence that reveals cosmic history and structure. This scenario illustrates how cosmic acceleration gradually erases information. The universe isn't just expanding. It's actively destroying the evidence of its own history and extent. Future civilizations will know less about the cosmos than we do, not because they're less advanced, but because the information has literally expanded away. This raises an interesting question. Are we in a similar position? Have we already lost access to evidence that earlier observers might have seen? The universe is 13.8 billion years old. Intelligence might have arisen earlier in cosmic history on planets around older stars. If advanced civilizations existed billions of years ago, they might have observed phenomena that are now beyond our horizon. The cosmic microwave background was brighter in the past. The evidence for the Big Bang was clearer. Distant galaxies were more numerous and easier to observe. Early civilizations might have had better data about cosmic origins than we have. As the universe aged, some of that information faded. We're working with degraded evidence compared to what earlier observers might have accessed. This creates a kind of cosmic FOMO, a fear of missing out on knowledge that once existed but is now gone. We can't recover lost information about regions that have slipped beyond the event horizon. We can't undo the effects of cosmic expansion. We're stuck with the evidence available in our particular cosmic epoch. On the other hand, we're fortunate to exist when we do. The universe is old enough for complex chemistry and biology to have developed. Stars have had time to forge heavy elements and distribute them through supernovae. Planets have formed and cooled. Life has emerged and evolved into intelligence. These processes take billions of years. We couldn't exist much earlier in cosmic history, but we also exist before the universe has expanded so much that evidence becomes too sparse. We can still see the cosmic microwave background. We can still observe distant galaxies from various epochs. We have access to a rich tapestry of information spanning billions of years of cosmic history. In this sense, we occupy a privileged moment, a window when both sufficient time has passed for life to arise and sufficient evidence remains to understand cosmic origins. This window won't last forever. As billions of years pass, the universe will become increasingly dark and empty from any observer's perspective. Galaxies will slip beyond event horizons. Stars will exhaust their fuel. The cosmos will fade toward heat death, a state of maximum entropy where no energy flows and no complex structures can persist. In that far future, roughly 100 trillion years from now, the last stars will flicker out. Galaxies will contain only dead remnants, white dwarfs, neutron stars, black holes. The temperature of the universe will approach absolute zero. The cosmic microwave background will be redshifted to wavelengths spanning light years, undetectable by any conceivable instrument. Any observers existing in that era would face profound isolation. They would see no stars, no galaxies, no evidence of cosmic structure. They would exist in near total darkness, isolated in time as well as space. The cosmic horizon would have completed its work, separating all structures into causally disconnected patches too far apart to ever interact again. This ultimate fate highlights the temporary nature of cosmic structure. Galaxies, stars, and planets are temporary features, maintained by the flow of energy through the universe. As that energy disperses and spreads out, the structures dissipate. The universe returns to a simpler state, dark and cold, approaching but never quite reaching perfect uniformity. The cosmic horizon plays a central role in this dissolution. By preventing communication between distant regions, it ensures that the universe fragments into isolated patches. These patches can never coordinate, never share information, never merge back together. The acceleration driven by dark energy locks them into permanent separation. This fragmentation might seem pessimistic, a cosmic vision of isolation and decay. But it also highlights the remarkable circumstance of the present. We exist at a moment when the universe is rich with structure, filled with galaxies and stars, accessible to observation and study. We can ask deep questions about cosmic origins and have hope of finding answers. The cosmic horizon limits what we can know, but it doesn't eliminate knowledge entirely. We can still observe vast regions of space. We can still study the cosmic microwave background. We can still piece together the history of the universe from multiple lines of evidence. The horizon is a boundary, but it's not a wall. It's a limit that still permits substantial understanding. In some sense, the existence of the cosmic horizon makes our knowledge more precious. We know that future observers will have less access to cosmic information. We know that the evidence we can gather is temporary, destined to fade as expansion continues. This makes the scientific project more urgent. We have a limited window to study the universe before the evidence expands beyond reach. This perspective might seem anthropocentric, privileging our particular moment in cosmic history, but it's a consequence of physics, not human preference. The universe will be less observable in the future than it is now. That's a fact about cosmic expansion, not a value judgment. It means that if any era is privileged for studying cosmic origins, it's roughly now, give or take, a few billion years. We happen to exist in this window. Whether that's coincidence, necessity, or something more subtle remains an open question. But the fact remains that we occupy a moment when the universe is both old enough for intelligence to arise and young enough for cosmic evidence to remain abundant. The cosmic horizon limits what we can see, but it hasn't yet closed off too much of the cosmos from observation. Throughout this exploration, we've circled the cosmic horizon from many angles. We've examined its physical nature as a limit in time rather than space. We've considered how cosmic expansion and dark energy shape the horizon's evolution. We've explored the possibility that the observable universe is just one bubble within a larger multiverse. We've grappled with philosophical questions about the limits of knowledge and the nature of reality beyond observation. What have we learned? The cosmic horizon is not a place or a physical boundary. It's a consequence of the finite age of the universe and the finite speed of light. Information takes time to travel. The universe hasn't existed forever. These two facts combine to create a boundary beyond which we cannot see, not because our instruments are inadequate, but because the light hasn't had time to reach us. This boundary is constantly evolving. As the universe ages, the particle horizon expands. Light from slightly more distant regions completes its journey to us. The observable universe grows. But cosmic acceleration, driven by dark energy, works in the opposite direction. The event horizon contracts as expansion accelerates. Some galaxies currently visible will eventually slip beyond this boundary, their light stretched beyond detection. The cosmic horizon marks the edge of causality. Events beyond the horizon cannot affect us. Our actions cannot influence them. No signal, no light, no information of any kind can cross this boundary within the current age of the universe. Regions beyond the horizon are causally disconnected from our observable patch of space. Yet those regions almost certainly exist. The laws of physics shouldn't stop working beyond the horizon. Space probably continues, containing more galaxies, more stars, more structure. Whether space extends infinitely or curves back on itself at vast scales remains uncertain. But the observable universe is likely just a small sample of a much larger reality. This larger reality might include other bubble universes, regions where cosmic inflation ended at different times, and possibly with different physical constants. These bubbles would be separated by inflating space that expands faster than light, ensuring permanent isolation. No information could ever cross from one bubble to another. Each bubble would be its own causally closed universe. Whether this multiverse scenario is correct remains speculative, but it follows logically from our best theories of cosmic inflation and the early universe. If inflation is eternal, as many models suggest, then multiple bubbles are not just possible, but inevitable. The cosmic horizon would then mark not just the edge of our observable region, but potentially the edge of our entire bubble. The philosophical implications are profound. If regions beyond the cosmic horizon exist but can never be observed, are they meaningfully real? Can science make claims about unobservable regions? What does it mean for something to exist if it can never causally interact with us? These questions have no universally agreed upon answers. They touch on fundamental issues in philosophy of science and metaphysics. Most physicists adopt a pragmatic realism, assuming that the laws of physics we've tested continue to apply beyond the horizon. But they acknowledge the limits of verification. We can have justified confidence in what lies beyond, but we can never achieve certainty through observation. The cosmic horizon also highlights the temporary nature of cosmic structure and our privileged position in cosmic history. Future observers, billions of years from now, will have less access to cosmic information. The universe will appear emptier and darker from their perspective. They will lack key evidence about cosmic origins and large-scale structure. We exist in a window where both life can arise and cosmic evidence remains abundant. This is not coincidence so much as necessity. Intelligence requires billions of years to evolve, but if too much time passes, the evidence expands away. We necessarily find ourselves in an era where both conditions are met. This realization makes the scientific project more urgent and more precious. We have limited time to study the universe before key evidence fades beyond reach. The cosmic horizon is slowly but inexorably closing, cutting us off from more and more of the cosmos. What we learn now about cosmic origins and structure might become inaccessible to future civilizations. Yet even as the horizon limits what we can observe, it doesn't eliminate wonder or curiosity. We can still ask what lies beyond. We can still build theories and test their predictions within observable regions. We can still expand our understanding of cosmic history and structure. The horizon is a boundary, but boundaries can be understood. We might not be able to cross it, but we can study its nature and explore its implications. The cosmic horizon reminds us that the universe is larger than our ability to observe it. There are regions we will never see, questions we will never answer with certainty, phenomena that will forever remain beyond our reach. This is humbling, but it's also strangely comforting. The universe refuses to be fully captured by human understanding. There will always be more to discover, more to wonder about, more mysteries waiting beyond the horizon of knowledge. As we conclude this journey to the cosmic horizon, we're left with a sense of both accomplishment and incompleteness. We've explored the limits of observation and understanding. We've examined the physics that creates those limits and the philosophical questions they raise. We've considered what might lie beyond and why we can never know for certain. But the horizon itself remains untouched. It's still there, surrounding us in all directions, marking the boundary between the observable and the unobservable. It's still expanding in some senses and contracting in others, still evolving as the universe ages and expands. It's still the ultimate limit to human knowledge about the cosmos. And perhaps that's fitting. The universe doesn't owe us complete answers. It doesn't exist for our understanding or observation. The cosmic horizon is simply a feature of how reality works, a consequence of finite light speed and finite cosmic age. We're fortunate to exist at all, to be able to observe anything beyond our immediate surroundings, to piece together the history and structure of the universe from the light that reaches us. The horizon limits what we can see, but it doesn't limit what we can imagine, theorize, or wonder about. In that sense, the boundary between the observable and the unobservable is also a boundary between knowledge and imagination. Science takes us as far as observation allows. Beyond that lies the realm of possibility, where mathematics and physics can guide us, but observation cannot follow. We've reached the edge of what can be observed. The cosmic horizon represents a fundamental boundary, set by the age of the universe and the speed of light. Beyond it lies space we cannot see, regions that might extend infinitely in all directions, containing structures and galaxies we will never observe. But boundaries of one kind often reveal boundaries of another. The cosmic horizon is a boundary in space and time. There exist other boundaries in nature, places where the familiar rules break down and something stranger takes over. Regions where time itself behaves differently, where the flow of cause and effect becomes murky and strange. These regions exist not at the edges of the cosmos, but at the edges of matter itself. Places where gravity becomes so strong that not even light can escape, where space-time curves so severely that it forms a boundary as absolute as the cosmic horizon, but far more extreme in its implications. We'll explore these boundaries, these event horizons of a different kind, in our next journey. For now, rest with the knowledge that the universe is larger than what we can see, richer than what we can measure, stranger than what we can fully comprehend. The cosmic horizon marks the limits of observation, but the limits of understanding reach even further, into realms where space and time themselves become questions rather than answers. The cosmic horizon divides space into regions that can communicate and regions that cannot. This division reflects something fundamental about causality itself. Cause and effect require connection. Events must be able to influence each other for causal relationships to exist. The cosmic horizon marks where this ability breaks down. Light speed represents the maximum rate at which influence can propagate. When you flip a switch, the light doesn't instantly fill the room. It travels outward at 300,000 kilometers per second. This seems instantaneous for human perception, but it's finite. There's a brief moment when the far side of the room remains dark, while light crosses the intervening space. Scale this up to cosmic distances, and the delays become significant. Light from the sun takes 8 minutes to reach Earth. We see the sun as it was 8 minutes ago. If the sun suddenly vanished, we wouldn't know for 8 minutes. For that brief period, Earth would continue, orbiting what appeared to be a normal star, unaware that the gravitational and electromagnetic influences holding the solar system together had already ceased. This creates what physicists call a light cone. Imagine drawing a cone in space-time, with the present moment at its tip. The cone extends backward and outward, encompassing all events that could have causally influenced the present. This is your past light cone. Everything outside this cone happened either too far away or too recently to have affected you. Similarly, you can draw a future light cone extending forward from the present. This cone encompasses all events you could potentially influence. Everything outside this cone is too far away for your actions to reach before those events occur. You're causally disconnected from them, at least for now. The cosmic horizon represents the edge of your past light cone, stretched back to the beginning of time. It encompasses everything that could possibly have influenced you given the age of the universe and the speed of light. Beyond this horizon lie events and regions that are outside your past light cone entirely. They haven't had time to send light or any other signal to you yet. This creates a strange situation. Those distant regions exist right now, in the present moment, but they're not in your present in the causal sense. Your present consists of events connected to you by light signals. The regions beyond the horizon are simultaneous, with you in coordinate time, but they're not simultaneously accessible. They exist in a present you cannot observe or interact with. This raises questions about what simultaneous means. In relativity, simultaneity is not absolute. Different observers moving at different speeds disagree about which events happen at the same time. There's no universal now spanning the cosmos. Each observer has their own frame of reference, their own definition of simultaneous events. The cosmic horizon makes this relativity of simultaneity cosmically significant. When we talk about the observable universe being 93 billion light-years across, we're choosing a particular definition of simultaneity. We're imagining a cosmic time coordinate that extends across all of space, defining a universal present. In this framework, distant galaxies exist now at those enormous distances, but an observer moving at high velocity relative to us would define the present differently. They would calculate different distances to those same galaxies. The cosmic horizon would have a slightly different size and shape from their perspective. The boundary between observable and unobservable shifts depending on your motion through space. This doesn't mean the horizon is arbitrary or observer-dependent in some radical sense. All observers agree on the fundamental physics. All observers see light traveling at the same speed. All observers find themselves surrounded by a cosmic horizon beyond which they cannot see. Details vary slightly, but the underlying structure remains consistent. The cosmic horizon thus reflects the causal structure of spacetime itself. It's not an accident of our location or our technology. It's built into the geometry of the universe. Space and time combine into a four-dimensional structure with specific properties. Light travels at a fixed speed through this structure. The universe has a finite age. These facts together determine where the horizon forms and what it separates. Understanding causality helps clarify what lies beyond the horizon. Those regions are not in our causal past. Events there haven't had time to influence us, but they are in our causal future, at least in principle. Given enough time, light from slightly beyond the current horizon will eventually reach us. The particle horizon is always expanding, bringing new regions into observable range. The event horizon complicates this picture. Due to cosmic acceleration, some regions that are currently beyond our particle horizon will never become observable. They're not in our causal past, and they're not in our causal future either. They're permanently disconnected from us. The space between us and them is expanding faster than light can close the gap. This permanent disconnection is profound. It means the universe naturally fragments into causally isolated patches. No coordination is possible between these patches. They can never share information, never influence each other's evolution. They develop independently, following the same physical laws, but potentially creating very different structures depending on initial conditions. In some sense, each causally connected patch is its own universe. Not in the sense of having different physics, but in the sense of being a complete, self-contained region, where causes produce effects and events unfold in connected sequences. The regions beyond the event horizon are not part of your universe in this causal sense, even though they're part of the same spacetime. This fragmentation accelerates as cosmic expansion continues. More regions slip beyond event horizons. the causally connected patches shrink. Eventually, each galaxy or galaxy cluster becomes isolated, unable to influence anything beyond its local group. The universe dissolves into separate island universes, each containing only the matter gravitationally bound together. The cosmic horizon is therefore not static in its effects. It doesn't just limit what we can see. It actively shapes the causal structure of the universe over time. What begins as a single connected cosmos gradually fragments into disconnected regions, each evolving independently toward heat, death, and darkness. This fragmentation might seem like a loss, a dissolution of cosmic unity, but it also reveals something deep about the nature of space and time. The universe doesn't have to be causally connected across all regions. Connection requires communication, and communication requires time. As space expands and time progresses, the ability to maintain connections across vast distances disappears. The universe naturally separates into independent regions simply because of its expansion. Understanding this helps us think about what the cosmic horizon means. It's not just hiding distant galaxies from view. It's creating fundamental divisions in the causal structure of reality. Beyond the horizon don't just lie regions we can't see. They're regions we can never interact with, never influence, never receive signals from. They're outside our universe in the causal sense, even though they're part of the same spatio-temporal manifold. This might be the most profound implication of the cosmic horizon. It shows that the universe is not a single connected whole. It's a collection of overlapping regions, each causally connected within itself, but disconnected from regions beyond its horizon. We happen to exist within one such region. We can observe and influence only what lies within our cosmic horizon. Everything beyond remains forever separate, developing according to its own history, unreachable and unknowable. The picture we've developed relies on the standard model of cosmology. The universe began with a Big Bang. It's been expanding ever since. Dark energy accelerates this expansion. These assumptions lead directly to the existence of a cosmic horizon with the properties we've described. But what if these assumptions are wrong? Alternative cosmologies exist, frameworks that explain observations differently and make different predictions about what lies beyond the horizon. Examining these alternatives help clarify what we do and don't know about the universe's structure. One alternative proposes that the universe is eternal, without beginning or end. In these steady-state models, matter is continuously created as space expands, maintaining constant average density. The universe looks roughly the same at all times, with new galaxies forming to replace ones that move away due to expansion. There's no moment of creation, no early hot dense state, no cosmic microwave background from an epoch of recombination. Steady-state cosmology was popular in the mid-20th century. It appealed to some scientists because it avoided the philosophical difficulties of a cosmic beginning. If the universe has always existed, there's no need to ask what came before or what caused the Big Bang. Time extends infinitely into the past. The universe has no origin. But observations contradicted steady-state predictions. The cosmic microwave background, discovered in 1965, showed that the universe was once hot and dense. This radiation has no natural explanation in steady-state models. Additionally, distant galaxies look different from nearby ones, showing that the universe was different in the past. This contradicts the steady-state principle that the universe should look the same at all times. Modern observations have essentially ruled out steady-state cosmology in its original form, but they haven't eliminated all alternatives to the Big Bang. Some cosmologies propose that the universe undergoes cycles of expansion and contraction. The Big Bang wasn't a unique beginning, but rather the latest in an endless series of bounces. In cyclic models, the universe expands for trillions of years, then contracts back to a hot, dense state, then bounces and expands again. Each cycle might last 100 trillion years or more. We're currently in the expansion phase of one such cycle. The cosmic microwave background comes from the hot, dense state at the bounce, not from a unique beginning. Cyclic cosmologies face theoretical challenges. The laws of physics, as we understand them, don't easily permit a bounce. When matter contracts to high density, general relativity predicts a singularity, a breakdown of spacetime where density and temperature become infinite. Bouncing through a singularity requires new physics, perhaps from quantum gravity theories that haven't been fully developed. Some versions of string theory allow for cyclic universes. In these models, the universe is a brain, a membrane-like object existing in higher dimensional space. Cycles occur when our brain collides with another brain, creating the hot, dense state that appears to us as a Big Bang. The collisions happen periodically, driving cycles of expansion and contraction. If the universe is cyclic, the cosmic horizon takes on different meaning. It still limits what we can observe based on light travel time and cosmic age. But beyond the horizon might lie regions in different phases of the cycle. Some areas might be contracting while we're expanding. The overall structure would be far more complex than simple expansion from a single Big Bang. Another alternative cosmology suggests we live in a simulation or constructed reality. If some advanced civilization has the ability to create detailed simulations of entire universes, we might be living inside one. The cosmic horizon might represent the computational boundary of the simulation. Beyond it lies not more space, but simply unrendered territory, regions. The simulation hasn't bothered to calculate, because no observer is looking at them. This simulation hypothesis is difficult to test, because a sufficiently advanced simulation could mimic real physics perfectly. If the simulation is designed well, we'd have no way to detect that we're inside it. The hypothesis also raises the question of what simulates the simulators. Are they in a real universe or another simulation? The question regresses without clear resolution. Most physicists regard simulation hypothesis as interesting philosophy, but not particularly useful science. It doesn't make specific testable predictions that differ from standard cosmology. It adds an extra layer of explanation without adding explanatory power. For practical purposes, we treat the universe as real and study the physics we observe. Yet another alternative involves the universe being embedded in a larger structure. We might inhabit a lower dimensional slice of a higher dimensional space. The cosmic horizon would then mark the edge of what we can see within our slice. But more universe might exist in the extra dimensions we can't access. Theories with extra dimensions, particularly those arising from string theory, suggest that familiar three-dimensional space might be embedded in a higher dimensional bulk. Gravity can propagate through all dimensions, but other forces might be confined to our three-dimensional brain. This could explain why gravity is weaker than other forces. It leaks into extra dimensions while other forces remain confined. If extra dimensions exist, they're either very small, curled up on scales far smaller than atoms, or we're confined to a brain that prevents us from moving through them. Either way, we can't directly observe the extra dimensions. The cosmic horizon would mark our observational limit within the three dimensions we inhabit, while vast additional structure might exist in directions we can't access. These alternative cosmologies share a common feature. They complicate the question of what lies beyond the cosmic horizon. In standard Big Bang cosmology, the answer is probably more of the same. More galaxies following similar patterns. In cyclic models, different regions might be in different phases. In embedded models, other structures might exist in dimensions we can't perceive. In simulation models, there might be nothing beyond the horizon except unrendered computational space. We can't currently distinguish these alternatives observationally. They make similar predictions about what we observe within the cosmic horizon. The differences appear mainly in how they interpret that observations and what they predict about unobservable regions. Without access to those regions, we can't definitively rule out alternatives. This epistemic limitation is frustrating but important. It reminds us that cosmology, despite its successes, deals with extrapolations far beyond direct observation. We observe one region of space at one moment in cosmic history. From this limited sample, we infer the structure and evolution of the entire universe. That inference relies on assumptions about uniformity and universality of physical law. These assumptions are reasonable. The universe appears uniform at large scales. Physical constants seem to have the same values everywhere we can measure them. Light from distant galaxies shows the same spectral lines, indicating the same atomic physics. All evidence suggests the universe is homogeneous and isotropic beyond what we directly observe. But assumptions are not proof. Alternative cosmologies remind us that other frameworks might fit the data. The cosmic horizon enforces humility. We cannot check our assumptions about regions beyond our observational reach. We might be right that the universe continues uniformly into the distance, or we might be missing something important that only becomes apparent at scales far exceeding the observable universe. For practical purposes, cosmologists work with the standard model because it fits observations well and makes testable predictions. But the existence of alternatives keeps the field honest. It reminds us that our picture of the cosmos is provisional, subject to revision if new evidence emerges. The cosmic horizon might hide surprises. What lies beyond might not be what we expect. The cosmic horizon is fundamentally temporal. It marks how far back in time we can see, limited by the age of the universe and the speed of light. This temporal nature connects the horizon to one of physics' deepest mysteries, the arrow of time. Time appears to flow in one direction. Causes precede effects. Eggs break, but don't spontaneously reassemble. Heat flows from hot to cold, not the reverse. Memory records the past, but not the future. These phenomena all point toward a directional flow of time, an asymmetry that distinguishes past from future. Yet the fundamental laws of physics are time-symmetric. Newton's laws work equally well forward or backward in time. Maxwell's equations for electromagnetism are time-reversible. Even quantum mechanics and general relativity show time symmetry at their core. If you filmed particle interactions and played the film backward, the reversed motion would still obey the same physical laws. This creates a puzzle. If the laws of physics don't prefer one time direction over another, why does the universe so obviously have an arrow of time? Why do we remember the past but not the future? Why does entropy increase as time progresses? The answer lies in boundary conditions. The universe began in a low entropy state. The early universe was remarkably uniform, with matter distributed smoothly, except for tiny quantum fluctuations. This smoothness represents low entropy, because there are relatively few ways to arrange matter uniformly compared to the many ways to arrange it in clumps and structures. As time progressed, gravity amplified those tiny fluctuations. Matter clumped together into galaxies and stars. The uniform distribution broke down into complex structures. This represents an increase in entropy, a movement toward more probable arrangements of matter. The arrow of time emerges from this entropy gradient. Time flows in the direction of increasing entropy. The cosmic horizon connects to this arrow because it marks the beginning of time itself. We can't see beyond the Big Bang because there was no before. Time began with the universe. The horizon represents the temporal origin, the point where the entropy gradient starts. If the universe were eternal, there would be no beginning and possibly no arrow of time. Entropy would have increased forever into the past, making the distant past infinitely high entropy. But observations show low entropy in the early universe, suggesting a beginning where entropy was minimized. This low entropy beginning is itself puzzling. Why did the universe start in such a special, unlikely state? If we randomly selected a moment from all possible configurations of matter and energy, we'd almost certainly get a high entropy state, with matter dispersed uniformly and energy spread thin. The fact that we find ourselves near the beginning of a low entropy universe seems improbable. Some cosmologists argue that the low entropy beginning is explained by inflation. The inflationary epoch stretched space smooth, erasing earlier irregularities and creating the uniform state we observe in the cosmic microwave background. Inflation acts as an entropy reset, producing low entropy regardless of what came before. But inflation itself requires explanation. Why did inflation occur? What set its initial conditions? These questions push the explanation back without fully resolving it. The arrow of time and the low entropy beginning remain somewhat mysterious even with inflation. The cosmic horizon divides time into observable past and unobservable future. We can look backward toward the Big Bang, observing earlier and earlier epochs as we gaze at more distant objects. But we can't see forward into the future. Time flows inexorably from past to future, carrying us along. The horizon marks the earliest moment we can observe, the temporal beginning of the observable universe. This temporal boundary affects how we understand causation. Events within our past, light cone could have caused what we observe now. Events in our future light cone might be caused by what happens now. But events outside our light cone entirely are causally disconnected. They can't cause anything we observe, and we can't cause anything that happens there. The cosmic horizon thus defines the temporal extent of causality. It's not just a spatial boundary. It's a limit on how far back in time we can trace causes and how far forward we can project effects. The universe's finite age creates a temporal horizon, just as light's finite speed creates a spatial one. Thinking about the cosmic horizon temporally also clarifies what it means for regions to be beyond it. These regions exist in the present, but they're not in our causal past. We can't see them because light from those regions hasn't had time to reach us. The delay is temporal, not spatial. If we wait long enough, light from slightly beyond the current particle horizon will eventually arrive. The horizon is expanding, slowly revealing new regions. But the event horizon works differently. Regions beyond the event horizon will never become observable, not because of insufficient time, but because space expands too rapidly. The temporal limit combines with spatial expansion to create permanent causal disconnection. This interplay between time and space in defining the horizon reflects the unity of spacetime. We can't really separate spatial distance from temporal duration at cosmic scales. When we say a galaxy is 10 billion light-years away, we're describing both a distance and a time. The light traveled for 10 billion years, during which the galaxy receded due to cosmic expansion. The cosmic horizon thus represents a boundary in space-time, not just space or time individually. It marks the limit of causal connection in four-dimensional spacetime. Events within this boundary can affect us. Events outside cannot. The arrow of time ensures this boundary has a particular direction. We can observe the past, but not the future. The horizon extends backward toward the Big Bang, not forward toward future epochs. Understanding the arrow of time helps explain why the cosmic horizon matters. If time were symmetric, we might be able to observe both past and future, both the Big Bang and the far future state of the cosmos. But time's arrow restricts our observation to the past light cone. We see where we've been, but not where we're going. This makes the horizon a one-way boundary. Light crosses it from the outside to the inside, revealing distant regions. But information can't flow from inside to outside, at least not backward in time. The horizon is permeable in one direction and impermeable in the other, following the arrow of time. The arrow of time also affects what the horizon conceals. We can't see regions beyond the horizon partly because their light hasn't reached us yet. But we also can't see them because seeing requires receiving light, and receiving is a time asymmetric process. We absorb photons that traveled from past to future. We can't absorb photons from the future because they haven't been emitted yet. These considerations intertwine the cosmic horizon with fundamental questions about time. The horizon marks a temporal boundary as much as a spatial one. It divides the observable past from the unobservable past and future. It reflects the arrow of time, the entropy gradient, and the causal structure of spacetime. Understanding the horizon requires understanding time itself, and vice versa. Throughout this exploration, we've grappled with a fundamental question. What does it mean to say that regions beyond the cosmic horizon exist, if we can never observe them, never interact with them, never receive any signal from them? In what sense are they real? This question divides into two philosophical positions. Realism holds that reality exists independently of observation. The universe is out there whether we observe it or not. Physical laws operate everywhere, not just in the regions we can see. Galaxies beyond the cosmic horizon are just as real as galaxies within it, even though we can never detect them. Instrumentalism takes a more cautious stance. Science deals with observations and predictions. Theories are tools for organizing data and making testable forecasts. Claims about unobservable regions are only meaningful if they affect observable predictions. If a theory makes identical predictions within the observable universe regardless of what lies beyond the horizon, then those beyond the horizon claims add nothing to the theory's scientific content. Most working physicists lean toward realism in their intuitions. When a cosmologist says the universe extends far beyond the cosmic horizon, they typically mean this literally. They're not just making claims about mathematical models. They believe those distant galaxies really exist, following the same physics, forming similar structures, evolving according to the same laws. This realist stance is supported by the uniformity of physics. Every test we've ever performed shows that physical laws work the same everywhere within the observable universe. The speed of light is constant. Gravity follows the same equations. Atoms emit the same spectral lines. This uniformity suggests that physics doesn't magically change beyond the cosmic horizon. The universe probably continues, governed by the same laws, containing similar structures. But instrumentalists point out that this argument involves extrapolation beyond evidence. We've tested physics extensively within the observable universe. We have no evidence about what happens beyond the horizon. Maybe the universe continues uniformly. Maybe it doesn't. Maybe there's no meaningful sense in which anything exists beyond our causal patch. We can't know because we can't observe. This divide reflects deeper disagreements about scientific method. Should science restrict itself to claims about observables? Or can science legitimately make claims about unobservable reality, provided those claims follow logically from well-tested theories? The cosmic horizon brings these questions into sharp focus because it creates a clear boundary between observable and unobservable. Within the horizon, we can test theories, gather evidence, make measurements. Beyond the horizon, theories make predictions, but we can never verify them. Consider the claim that the universe is infinite. This follows naturally if space is flat and extends uniformly beyond the observable region. But we can never verify infinity. We observe only a finite portion of space. The claim about infinity is an extrapolation, justified by uniformity arguments, but never directly tested. A realist would say infinity is either true or false, as a matter of fact, independent of whether we can verify it. An instrumentalist might say the question isn't really scientific, because it can't be answered observationally. The claim about infinity doesn't affect any measurement we can make. It's metaphysical rather than physical. Similar debates arise about the multiverse. If eternal inflation creates countless bubble universes beyond our horizon, do those bubbles really exist? Realists would say yes. They're natural consequences of well-tested inflation theory. Instrumentalists would say we can only confirm inflation's predictions within our observable universe. Claims about other bubbles might follow mathematically, but they're not meaningfully scientific because they're not testable. These philosophical differences matter because they affect how we interpret cosmology. A realist cosmology makes bold claims about the full extent of reality, using observations as windows into a much larger structure. An instrumentalist cosmology restricts itself to claims about observables, treating theories as organizing frameworks rather than descriptions of transcendent reality. Neither position is obviously right or wrong. They represent different approaches to science, different ways of thinking about the relationship between observation and reality. Both positions can accept the same observational evidence while interpreting it differently. For our purposes, the important point is that the cosmic horizon marks where these philosophical differences become consequential. Within the horizon, realists and instrumentalists largely agree. Both accept observational evidence. Both use theories to organize and predict. The differences emerge when considering what lies beyond observation's reach. This makes the cosmic horizon not just a physical boundary, but an epistemological one. It marks the limit where certain types of knowledge become impossible. We can have justified beliefs about what lies beyond. We can build theories that naturally extend beyond the horizon, but we can't have observational knowledge in the traditional scientific sense. This epistemological limit is permanent. No technological advance can push the cosmic horizon farther. The limit is set by the age of the universe and the speed of light, fundamental features of spacetime itself. Unless those features somehow change, the horizon will always exist, always separating what can be known observationally from what must remain inferential. Different people find this limit comforting or frustrating. Some appreciate the boundary because it reminds us that reality exceeds human knowledge. The universe is larger and richer than what any mind can fully grasp. Others find it frustrating because science thrives on testing and verification. A boundary beyond which no testing is possible feels like a limitation on scientific method itself. Both reactions are valid. The cosmic horizon does limit science in one sense. It creates questions we can formulate but never answer observationally. Yet it also reveals something profound about the universe's structure. The fact that boundaries exist, that not everything is knowable, tells us something important about the nature of space, time, and causality. Perhaps the deepest lesson is that reality is not identical with observability. Things can be real without being observable. The cosmic horizon might hide vast regions of space, countless galaxies, possibly even other bubble universes with different physics. These regions are real in the sense that they exist in space-time, follow physical laws, and evolve according to causal processes. But they're not observable from our location in space-time. This distinction between real and observable is humbling. It reminds us that observation is a local phenomenon. We observe from a particular place at a particular time. What we can see depends on where and when we are. Other observers in other locations would have different cosmic horizons, able to see regions we can't, and unable to see regions we can. In this sense, the observable universe is not the universe. It's the portion of the universe accessible from Earth in the early 21st century. Other portions exist but remain beyond our reach. The cosmic horizon is observer-dependent in its location, even though the underlying physics creating horizons is universal. This observer dependence doesn't make the horizon subjective or arbitrary. All observers agree on the physics. All observers find themselves surrounded by horizons. The details vary, but the structure is consistent. The cosmic horizon reflects objective features of spacetime, while manifesting differently for different observers. Understanding this helps resolve some of the tension between realism and instrumentalism. Realists are right that regions beyond the horizon probably exist and probably contain more galaxies. Instrumentalists are right that we can't verify this and should be cautious about claims concerning unobservables. Both perspectives capture something true about science and the cosmic horizon. The cosmic horizon carries philosophical weight beyond its physical properties. It shapes how we think about humanity's place in the universe and the ultimate fate of intelligence and consciousness. If the universe extends infinitely beyond the cosmic horizon, or if it contains countless bubble universes in an eternal inflation scenario, then Earth and humanity are infinitesimally small parts of an incomprehensibly vast reality. Not just small in the sense that Earth is a tiny planet orbiting an ordinary star, but small in the sense that our entire observable universe, containing trillions of galaxies, might be a negligible fraction of all that exists. This realization can be humbling or terrifying depending on temperament. It suggests that nothing happening on Earth or even in our galaxy has any significance for the larger cosmos. We're isolated in our corner of space, unable to communicate with or influence the vast majority of reality. Our actions, our civilizations, our entire history plays out on an infinitesimal stage, mattering only to ourselves. Yet this cosmic insignificance might also be liberating. If the universe is vast and indifferent, then we're free to create our own meaning and purpose. There's no cosmic script we must follow, no grand plan we must serve. We can explore, create, and flourish simply because we exist and have the capacity to do so. The cosmic horizon ensures that our region of space is ours alone, to shape as we see fit. The horizon also affects how we think about humanity's long-term future. As cosmic expansion continues and galaxies slip beyond the event horizon, the observable universe will gradually empty. In the far future, only the galaxies gravitationally bound to our local group will remain visible. Humanity's descendants, if any exist, will be confined to this small island in an increasingly dark cosmos. This long-term isolation might seem bleak, but it's also billions of years away, time enough for countless generations to live, explore, and thrive the universe won't become truly empty for trillions of years. That's enough time for civilizations to rise and fall repeatedly, for life to spread across millions of star systems, for minds to evolve in directions we can't currently imagine. The cosmic horizon also raises questions about contact with other intelligent species. If intelligence exists elsewhere in the universe, is it within our cosmic horizon or beyond it? If beyond, we can never communicate. If within, communication might be possible, but faces enormous challenges of distance and time. The Drake equation attempts to estimate the number of intelligent civilizations in our galaxy capable of communication. Even optimistic estimates suggest they're rare and far between. Communication across interstellar distances would take years or centuries even at light speed. Across intergalactic distances, it would take millions or billions of years. And across distances approaching the cosmic horizon, communication becomes impossible because signals would be redshifted beyond detection before arriving. This suggests that even if intelligence is common in the universe, most civilizations are permanently isolated from each other. The cosmic horizon fragments space into regions that can never establish contact. Each region develops independently, creating unique cultures and technologies, exploring the cosmos from their own perspectives, never knowing about the countless other civilizations doing the same thing beyond the horizon. This cosmic loneliness might be the natural state of intelligence in an expanding universe. Brief windows of local contact might occur when civilizations arise in the same galaxy or nearby galaxies. But cosmic-scale communication, exchange between civilizations in distant galaxy clusters, seems impossible given the structure of space-time and the accelerating expansion of space. Some philosophers find this isolation depressing. They imagine a future where humanity expands across the stars, but never encounters other intelligence, forever alone in a vast empty cosmos. Others find it oddly comforting. If we're alone, then our existence is rare and precious. We're not just one of countless civilizations. We might be one of very few, perhaps one of only a handful in the observable universe. The truth might lie somewhere between these extremes. Intelligence might be neither vanishingly rare nor common. It might exist in scattered pockets throughout the cosmos, each pocket isolated by cosmic expansion and vast distances. We share the universe with others, but can never meet them, never share knowledge or culture, never compare notes on our respective explorations of reality. The cosmic horizon thus shapes the existential context of intelligence. It defines the limits of possible connection and communication. It ensures that no matter how far we travel or how advanced we become, most of the universe will always remain beyond reach. We're confined to our causal patch, our local region of space-time, able to observe and influence only a tiny fraction of all that exists. This confinement might seem limiting, but it also defines the scope of our concerns. We can't affect what happens beyond the cosmic horizon. We can't save civilizations in distant galaxy clusters or prevent catastrophes in other bubble universes. Our responsibility extends only to our observable region, the part of reality we can actually influence. In this sense, the cosmic horizon creates a natural boundary for ethics and responsibility. We're responsible for what we can affect, which means our local region of space and the future light cone extending from the present moment. Beyond that, we're observers only, able to learn from what we see, but unable to change or influence distant events. This boundary might make the ethical project more manageable. Instead of worrying about an infinite universe full of beings we can never help, we can focus on the finite region we actually inhabit. The cosmic horizon defines our sphere of influence and thus our sphere of responsibility. What happens beyond it unfolds independently of our choices. We've journeyed far in our exploration of the cosmic horizon. We've examined its physical basis in light speed and cosmic expansion. We've considered what might lie beyond, from simple extensions of our observable universe to exotic multiverse scenarios. We've grappled with philosophical questions about reality and observation, about time and causality, about meaning and isolation in a vast cosmos. What have we learned? The cosmic horizon is real, fundamental, and permanent. It's not a temporary limit that better technology might overcome. It's built into the structure of spacetime itself, a consequence of finite light speed and finite cosmic age combined with the expansion of space. This horizon divides space into regions that can communicate and regions that cannot. Within the horizon, we can observe, measure, and test theories. Beyond it lies space we can infer but never directly observe. This creates an epistemological boundary, a limit to what we can know through observation alone. Yet the horizon is not static. It evolves as the universe ages. The particle horizon expands, revealing new regions as light from farther away completes its journey. The event horizon contracts, cutting us off from regions that are receding too rapidly for their light to ever reach us. The boundary breathes with the expansion of space, growing in some senses and shrinking in others. What lies beyond the horizon probably resembles what lies within. More galaxies, more stars, more planets, all following the same physical laws. The universe appears uniform at large scales within the observable region. This uniformity probably continues beyond the horizon. Space extends, possibly infinitely, containing structures similar to those we observe nearby, but probably is not certainly. The horizon might conceal surprises. Other bubble universes with different physics might exist in an eternal inflation scenario. The universe might have large-scale patterns or features only apparent across distances far exceeding the observable region. We can't rule out alternatives because we can't observe beyond the boundary. This uncertainty is both frustrating and appropriate. The cosmic horizon reminds us that knowledge has limits. We're embedded in the universe, observing from a particular place and time. Our observations are necessarily local and limited. We can reason beyond those limits, but we can't verify our conclusions directly. The horizon also shapes the human condition in subtle ways. It defines the scope of possible communication and influence. It isolates civilizations from each other if they're sufficiently distant. It ensures that most of the universe will always remain mysterious and unreachable. We're confined to our causal patch, able to explore only a tiny fraction of reality. Yet this confinement is not imprisonment. Within the cosmic horizon lies vast space to explore, countless stars to study, perhaps other life to discover. The observable universe contains challenges and mysteries enough to occupy humanity for billions of years. The existence of unreachable regions beyond doesn't diminish the richness of what lies within reach. As we conclude this exploration, we return to the question that began our journey. What lies beyond the farthest edge of the observable universe? The honest answer is we don't know for certain. We have theories, models, reasonable extrapolations from observable data. But the cosmic horizon prevents direct verification. We can say with confidence that something lies beyond. Space probably continues. The laws of physics probably still apply. Matter and energy probably exist in familiar forms, arranged into galaxies and stars. The horizon hides not complete mystery but simply more universe, regions similar to what we already observe. But we can also acknowledge the limits of our knowledge. The horizon marks where observation ends and inference begins. We can peer to the edge of observability and extrapolate beyond, but we can't cross the boundary ourselves. The regions beyond remain forever inaccessible, forever mysterious in their details, if not in their probable general character. This combination of knowledge and ignorance, confidence and uncertainty, defines humanity's relationship with the cosmos. We know vast amounts about the universe's structure and history. We can trace cosmic evolution from the Big Bang through the formation of galaxies and stars to the emergence of life and intelligence. We understand the laws governing matter and energy across immense scales of space and time. Yet we also know that our understanding is incomplete. The cosmic horizon ensures that most of the universe lies beyond observation. Dark energy accelerates expansion for reasons we don't fully comprehend. The Big Bang itself emerged from conditions we can't quite explain. Questions remain unanswered, and some might remain unanswerable forever. The cosmic horizon thus represents both achievement and limitation. Achievement because we've understood its nature through observation and theory, despite being unable to cross it. Limitation because it marks where understanding necessarily becomes speculative, where verified knowledge gives way to informed conjecture. Perhaps this is fitting. Reality should exceed human comprehension. The universe should contain more than what any mind can fully grasp. The cosmic horizon reminds us of our place in the grand scheme. Simultaneously tiny and privileged, confined and free, knowledgeable and ignorant, we stand at a unique moment in cosmic history. The universe is old enough for intelligence to have arisen, but young enough for the cosmic microwave background and distant galaxies to remain observable. We can piece together the universe's history and structure from abundant evidence. Future observers, billions of years from now, will have less access to this information. They'll see a lonelier, darker cosmos. This makes our current era special. Not because we're cosmically significant in some grand sense, but because we live when cosmic evidence is plentiful and accessible. We can study the universe's origins. We can observe the cosmic horizon directly through the ancient light reaching our telescopes. We can understand, as well as anyone ever will, what lies at the boundary between the observable and the unreachable. The cosmic horizon marks the limit of what can be seen. Beyond it lies space we cannot observe, galaxies we cannot study, phenomena we cannot directly measure. This boundary is permanent, set by the fundamental structure of space and time. Yet even as the horizon limits observation, it doesn't limit imagination or curiosity. We can still ask what lies beyond. We can still build theories that naturally extend past the boundary. We can still satisfy ourselves that we understand the nature of the limit, even if we can't cross it. The universe is larger than human knowledge. It contains regions we'll never see, structures we'll never study, perhaps even life we'll never encounter. The cosmic horizon ensures this permanent unknown, this eternal mystery at the edge of observability. But mystery is not absence. The regions beyond the horizon are real, populated with matter and energy, governed by natural law. They're simply beyond our reach, separated from us by insurmountable barriers of space, time, and cosmic expansion. As we rest here at the boundary, contemplating the unreachable distance, we can find satisfaction in what we've learned. The cosmic horizon is understood. Its nature, its causes, its evolution through time. All these things are known. We cannot cross the boundary, but we comprehend it. That understanding represents a kind of victory, a triumph of reason over the limits of observation. The horizon will always be there, surrounding us in all directions, marking the edge of what light has revealed. Beyond it lies the great unknown, vast and mysterious and forever out of reach. But the boundary itself is knowable, and in knowing it, we know something profound about the structure of reality. Sleep well with this knowledge. The universe extends far beyond what we can see. Most of reality remains hidden behind the cosmic horizon, but the visible portion is vast and rich, full of wonders waiting to be discovered. The limit of observation is also an invitation to explore everything within reach. The cosmic horizon represents not an ending, but a beginning. It marks where certain questions become unanswerable, but also where answerable questions abound. Within the observable universe lies more than enough to occupy human curiosity for ages to come. And beyond the horizon, more universe probably, more galaxies following familiar patterns, more stars burning in the darkness, more structure and complexity arising from simple laws. The same reality we observe nearby, extended across distances we cannot measure, continuing beyond what light can show us. The cosmic horizon is the boundary we can never cross, but it's also the limit we can understand, the edge we can study and characterize and comprehend. In that understanding lies a deep satisfaction, a sense that even though we cannot see everything, we can at least understand why observation has limits. Rest now with this understanding. The universe is larger than human knowledge, vaster than human exploration, richer than human imagination. The cosmic horizon marks where observation ends, but where wonder continues. Beyond it lies the infinite unknown, forever mysterious, forever unreachable, forever there. Time transforms everything, including the cosmic horizon. Over billions and trillions of years, the boundary between observable and unobservable space will shift dramatically. Understanding this evolution helps us appreciate the temporary nature of our current observational privileges. The observable universe is currently about 93 billion light-years across. This size reflects both the age of the universe and the effects of cosmic expansion. As time progresses, the particle horizon will continue expanding. Light from more distant regions will complete its journey to us. In principle, the observable universe should grow larger as the universe ages, but cosmic acceleration complicates this picture. Dark energy is causing expansion to accelerate. The space between galaxies grows faster over time. This acceleration affects which regions we'll ever be able to observe. While the particle horizon expands, the event horizon contracts. Some galaxies currently visible will eventually slip beyond reach. Consider a galaxy 10 billion light-years away. We see it as it was 10 billion years ago, because that's how long its light took to reach us. In the billions of years since that light was emitted, the galaxy has receded due to cosmic expansion. It's now perhaps 15 billion light-years away in co-moving coordinates. As more billions of years pass, that galaxy will continue receding. If expansion continues accelerating, the galaxy will eventually cross the event horizon. From our perspective, it will appear to slow down, redshift dramatically, and fade from visibility. Its light, stretched to extreme wavelengths by expanding space, will become undetectable. This process is irreversible. Once a galaxy crosses the event horizon, no new light from it can ever reach us. The last photons from that galaxy, emitted just before it crossed the boundary, will arrive billions of years from now. After that, nothing. The galaxy will have vanished from the observable universe, not because it ceased to exist, but because space between us and it is expanding too rapidly for light to bridge the gap. Multiply this scenario across billions of galaxies. Over deep time, the observable universe will gradually empty. Galaxies beyond our local gravitationally bound group will recede beyond the event horizon one by one. The cosmic horizon will tighten around us, cutting us off from the vast majority of the universe. Astronomers billions of years from now, if any exist, will face a profound information loss. They won't be able to observe most galaxies we can see. The cosmic microwave background will have redshifted beyond detection. Evidence for the Big Bang will be subtle and indirect. They might struggle to reconstruct cosmic history from the limited evidence available. This future astronomer might look at their local group of galaxies and conclude they represent the entire universe. Without access to distant galaxies, without the cosmic microwave background, without clear evidence of cosmic expansion, they might develop very different cosmological theories. They might think the universe is small, static, and eternal. They would be wrong, but they would lack the evidence to know it. This scenario illustrates how cosmic horizons affect not just what we observe, but what future observers can discover. Information is not eternal. Evidence can be lost. The universe actively erases its own history through expansion. What we can learn now might become unknowable later. This makes our current era cosmologically privileged. We exist when evidence is abundant. We can see the cosmic microwave background clearly. We can observe galaxies at various distances and epochs. We can reconstruct the universe's history from multiple independent lines of evidence. Future observers won't have these advantages, but our era is also privileged in another sense. The universe is old enough for complex chemistry and biology to have developed. Elements heavier than hydrogen and helium were created in stars and supernovae over billions of years. Planets formed from this enriched material. Life arose and evolved into intelligence. This process takes time, lots of time, more time than the early universe could provide. So we necessarily exist in an era when the universe is old enough for life, but young enough for cosmological evidence to remain accessible. This balance between sufficient age and available evidence creates a relatively narrow window in cosmic history. We happen to occupy this window, not because we're special, but because intelligence can only arise when both conditions are met. Still, the window is closing. Each billion years that pass, more galaxies slip beyond the event horizon. More evidence fades beyond detectability. The window of rich cosmological observability is temporary, perhaps lasting only a few tens of billions of years in total. Before that, the universe was too young and hot for stars and life. After that, it will be too old and empty for comprehensive cosmological study. This temporal evolution of cosmic horizons connects to the arrow of time. The universe evolves from low entropy to high entropy, from organized structure to dispersed uniformity. Cosmic horizons participate in this evolution by fragmenting initially connected regions into isolated patches. What begins as a relatively uniform and connected cosmos ends as a collection of isolated island universes, each unaware of the others. The timescale for this fragmentation is enormous. The process takes trillions of years. Stars will exhaust their fuel long before galaxies finish slipping beyond horizons. The last stars will fade about 100 trillion years from now. Galaxies will contain only dead remnants for most of the universe's future existence. The cosmic horizon's evolution plays out against this background of stellar death and gradual darkening. In the very far future, perhaps 10 to the power of 100 years from now, even black holes will evaporate through Hawking radiation. The universe will contain only sparse particles and radiation, spread thin by relentless expansion. The temperature will approach absolute zero. The cosmic horizon will encompass only a tiny region around any remaining observers, if any exist. At that point, the horizon will have completed its work. The universe will be fragmented into causally disconnected patches, each containing only a handful of particles. No structure will remain. No energy will flow. The universe will have reached maximum entropy, heat death, the end of interesting cosmic evolution. This ultimate fate might seem depressing, but it's trillions upon trillions of years away. Between now and then lies an incomprehensibly long span of time during which stars will shine, galaxies will evolve, and perhaps countless civilizations will rise and fall. The cosmic horizon's gradual tightening is a very slow process on human timescales. Still, understanding this, evolution helps clarify the cosmic horizon's nature. It's not a fixed boundary. It responds to cosmic expansion and the universe's changing expansion rate. What we can observe today is different from what earlier observers could see, and different from what future observers will see. The horizon is dynamic, evolving along with the universe it defines. The cosmic horizon represents a classical limit to observation, one set by light speed and cosmic expansion. But quantum mechanics introduces additional limits that might affect what we can ultimately know about the universe. At extremely small scales, quantum uncertainty becomes significant. The Planck length, about 10 to the power of minus 35 meters, represents the scale where quantum effects on spacetime itself become important. Below this scale, the classical notion of smooth space and time breaks down. Space might become granular or foam-like. Time might not flow continuously. The concepts we use to describe larger-scale physics might not apply. This quantum limit affects how we think about the very early universe. The Big Bang represents an extrapolation backward in time to a moment when the universe was incredibly hot and dense. But we can't extrapolate all the way to infinite density or zero size. Quantum gravity effects should become important at the Planck scale, about 10 to the power of minus 43 seconds after the nominal Big Bang. Before this Planck time, our classical understanding breaks down. We can't say what the universe was like, or even if questions about time and space make sense in the usual way. The cosmic horizon, in a sense, extends backward to this Planck boundary. We can't see earlier because classical spacetime itself didn't yet exist in recognizable form. This creates a quantum horizon alongside the cosmic horizon. Just as we can't see beyond the cosmic horizon in space, we can't see before the Planck time in the early universe. Both boundaries mark limits to knowledge, though for different reasons. The cosmic horizon arises from finite light speed and expansion. The quantum horizon arises from the breakdown of classical concepts at extreme scales. These two horizons might be connected in subtle ways. Some theories of quantum gravity suggest that space itself has a minimum meaningful size, the Planck length. If so, there might be a maximum amount of information that can be contained in any region of space. This maximum density of information could limit what we can know about even regions within the cosmic horizon. The holographic principle, arising from black hole physics, suggests that all the information in a volume of space can be encoded on its boundary. If this principle extends to cosmic horizons, it might mean the observable universe contains a maximum amount of information determined by the horizon's surface area. This would limit not just what we can observe beyond the horizon, but how much detail we can ever know about anything. These quantum considerations don't change the basic picture of cosmic horizons. We still can't observe beyond the boundaries set by light speed and expansion. But they do suggest that even within the observable universe, there might be limits to how much detail we can extract. The universe might be fundamentally discrete at small scales, limiting the precision of any measurement. quantum entanglement adds another wrinkle. Entangled particles share quantum states in ways that correlate their properties even when separated by large distances. Some physicists have speculated about whether entanglement could somehow connect regions beyond the cosmic horizon. If particles that separated early in cosmic history remain entangled, they might share correlations even after expanding beyond each other's horizons. However, entanglement alone can't transmit information. The correlations exist, but you can't use them to send signals. Even if particles beyond the cosmic horizon are entangled with particles within it, we can't exploit this entanglement to learn about those distant regions. The no communication theorem of quantum mechanics ensures that entanglement doesn't violate the causal structure imposed by cosmic horizons. Still, the fact that quantum correlations might extend across cosmic horizons is conceptually interesting. It suggests that the universe might be more unified at quantum levels than classical horizons suggest. The separation of regions by cosmic expansion might be less absolute in quantum terms than in classical terms. Distant regions might be disconnected causally, but connected quantum mechanically in subtle ways. These quantum considerations also affect how we think about the multiverse. If bubble universes exist beyond our horizon, separated by inflating space, can they be entangled with each other? Some interpretations of quantum mechanics suggest that the entire universe, or even the entire multiverse, is a single quantum state. The separation into different regions or bubbles might be a classical illusion. At the deepest quantum level, everything might be unified in ways we don't yet understand. These ideas remain highly speculative. Quantum gravity is not yet a fully developed theory. We don't know for certain how quantum mechanics and general relativity combine at extreme scales. The relationship between quantum entanglement and cosmic horizons is not yet clear. These questions await future theoretical developments and possibly new observational tests. What we can say is that the cosmic horizon, while primarily a classical concept, might have quantum aspects that affect its ultimate meaning. The boundary between observable and unobservable might be more subtle in quantum terms than simple light speed limits suggest. The universe's quantum nature might create connections or correlations that transcend classical causal boundaries. For now, these remain interesting possibilities rather than established facts. The cosmic horizon, as we've described it, the boundary set by light speed and expansion, is well established observationally and theoretically. The quantum aspects are additions or refinements, not replacements for the classical picture. They might deepen our understanding without fundamentally changing the existence of observational boundaries. The cosmic horizon has profound implications for information theory. Information is physical. It's encoded in the states of matter and energy. When regions of space become causally disconnected, the information in those regions becomes inaccessible. The cosmic horizon thus represents an information boundary, as much as an observational one. Consider information about cosmic history. We can reconstruct the universe's past from evidence currently observable. The cosmic microwave background contains information about conditions 380,000 years after the Big Bang. Distant galaxies show us different cosmic epochs. Chemical abundances tell us about nucleosynthesis in the early universe. All this information is accessible because light from those epochs has reached us. But information about what's happening beyond the cosmic horizon right now is not accessible. Events occurring today in distant regions won't be observable for billions of years, if ever. If those regions are beyond the event horizon, information about them will never reach us. The information exists, but is causally disconnected from our region. This creates a kind of information horizon, not just an observational limit, but a limit on what information we can access even in principle. The information content of the observable universe is finite because the observable region is finite. Information beyond the horizon exists, but doesn't affect anything within it. In some sense, it doesn't exist for us because we can never interact with it. Entropy, the measure of disorder or information dispersal, increases over cosmic time. The early universe had low entropy. Matter was distributed uniformly. As time progressed, gravity amplified small fluctuations. Matter clumped into galaxies and stars. This clumping represents increasing entropy, even though it looks like increasing order. The apparent order is local. Globally, entropy increases as energy disperses and gradients flatten. The cosmic horizon affects entropy in subtle ways. As regions slip beyond the event horizon, the information they contain becomes permanently inaccessible. From our perspective, this information is effectively lost. The observable universe contains less information about the total universe as more regions become disconnected. This information loss mirrors what happens at black hole event horizons. When matter falls into a black hole, information about that matter becomes inaccessible to outside observers. The black hole horizon hides information from the external universe. Similarly, the cosmic horizon hides information about distant regions from our local region. Some physicists worry about whether information is truly lost in these cases or merely hidden. Information conservation is a principle in quantum mechanics. If information can be destroyed by cosmic expansion or black hole formation, that might violate quantum mechanical principles. Resolving this tension is an active area of research. One possible resolution involves the holographic principle. If all information in a region is encoded on its boundary, then nothing is truly lost. The information about regions beyond the cosmic horizon might be encoded on the horizon itself, like information about black hole interiors is encoded on the event horizon. We can't access the distant regions, but the information about them exists in principle, encoded in the structure of the horizon. This idea remains speculative and is difficult to test, but it suggests the cosmic horizon might be more than a simple boundary. It might be a physical surface with information processing properties. The horizon might contain a complete description of everything beyond it, encoded in a format we don't yet understand. Another consideration involves the total information content of the universe. If the universe is infinite, it contains infinite information. The observable universe contains only a finite subset of this information. As cosmic expansion continues and more regions slip beyond the event horizon, the information accessible to us decreases over time. The ratio of accessible to total information approaches zero as time goes to infinity. This gradual information loss is part of the universe's evolution toward heat death. As entropy increases and structure dissipates, the information needed to describe the universe's state becomes simpler. The end state, maximum entropy, contains minimal information. Everything is uniform and featureless. There's nothing interesting left to describe or measure. The cosmic horizon participates in this information evolution by fragmenting the initially connected universe into separate regions. Information that was globally accessible becomes locally inaccessible. The universe doesn't lose information globally, but each local region loses access to information in other regions. From any local perspective, information appears to be draining away as the horizon tightens and fewer regions remain observable. This has practical implications for cosmology. As future astronomers lose access to distant galaxies and the cosmic microwave background, they lose information about cosmic history. They might be unable to reconstruct the Big Bang or understand cosmic expansion from their limited evidence. Information that we can currently gather will be permanently lost to them, not destroyed, but simply beyond reach. This makes scientific observation time-sensitive in a cosmic sense. There's a window when certain types of information are accessible. Before this window, the universe was too young and hot for observers to exist. After this window, the information will have expanded beyond reach. We happen to exist within the window, able to gather evidence that will eventually become inaccessible. Understanding information theory helps clarify what the cosmic horizon means. It's not just hiding distant galaxies from view. It's partitioning information into accessible and inaccessible sets. It's creating an information structure where some data can be shared within causal patches, while other data remains isolated in disconnected regions. The universe fragments informationally as it expands, with each fragment containing less information about the whole over time. Throughout this exploration, we've examined the cosmic horizon from many perspectives. We've considered its physics, its evolution, its implications for knowledge and observation. As we approach the end of this journey, it's worth reflecting on what it means to be aware of cosmic horizons at all. Human consciousness arose on a small planet orbiting an ordinary star in an unremarkable galaxy. For most of human history, we didn't know galaxies existed. We thought the universe was small, perhaps extending only to the visible stars. The concept of cosmic horizons would have been meaningless. Yet through observation, reason, and imagination, we've expanded our cosmic awareness. We discovered other galaxies. We measured cosmic distances. We detected the expansion of space. We developed theories of the early universe. We predicted and observed the cosmic microwave background. We've mapped the observable universe to astonishing precision. This expansion of awareness represents something remarkable. Beings confined to a single planet, observing through narrow electromagnetic windows, have constructed an understanding of cosmic structure spanning billions of light years and billions of years. We've traced the history of the universe from fractions of a second after the Big Bang to the present moment. We've understood our place in cosmic space and time, and now we understand the limits of that understanding. The cosmic horizon marks where our awareness necessarily ends. We've pushed observation to the edge of what's possible and recognized that a boundary exists beyond which observation cannot go. This recognition itself represents a kind of knowledge. We know what we cannot know. We understand the limits even if we can't cross them. This cosmic awareness is perhaps unique to intelligent observers. The universe presumably contains many lifeless planets where no mind reflects on cosmic structure. On Earth, consciousness arose and eventually developed the capacity to contemplate cosmic scales. We're part of the universe examining itself, matter organized in a particular way that permits self-reflection and awareness of cosmic context. The cosmic horizon shapes this awareness. It defines the maximum scope of possible knowledge. We can be aware of our local region in detail. We can infer what lies beyond based on uniformity and physical law. But we cannot be directly aware of most of the universe. Our awareness is necessarily local, confined to regions within our cosmic horizon. This might be a fundamental feature of consciousness in the cosmos. Any intelligent observer, wherever they exist, finds themselves surrounded by a cosmic horizon. Their awareness is local. Most of the universe remains beyond their direct observation. They can infer, theorize, and imagine, but they cannot observe everything. Consciousness is necessarily finite in its scope, even if the universe is infinite in extent. Some philosophers wonder if consciousness has cosmic significance. Are minds necessary for the universe to exist, or at least to be meaningful? Does the universe exist in some sense only when it's observed and comprehended? These questions blend physics with metaphysics and have no clear answers. What we can say is that consciousness changes the universe's relationship to itself. Lifeless matter simply exists, following physical laws without awareness or understanding. Conscious matter reflects on its own existence and context. It asks questions. It seeks patterns. It constructs models and theories. The universe becomes aware of itself through conscious observers. The cosmic horizon limits this self-awareness. The universe cannot fully comprehend itself because no observer can see all of it. Each conscious being has access only to their local region. The full picture, if there is one, requires combining perspectives from countless observers across vast regions of space. But cosmic horizons prevent this combination. Each observer remains isolated, unable to share information with observers in distant regions. This might mean the universe's self-awareness is necessarily fragmented and incomplete. No single perspective encompasses everything. Each local region can be understood by observers within it. But the full cosmic structure transcends any single awareness. The universe knows itself only partially through scattered local observers, never achieving complete self-comprehension. Or perhaps self-comprehension isn't the point. The universe exists whether or not anyone understands it. Consciousness might be a fortunate accident, matter self-organizing in ways that permit reflection and awareness. The cosmic horizon limits this awareness, but awareness is remarkable simply for existing at all, regardless of its scope. As conscious observers, we find ourselves in a strange position. We're part of the universe, made of the same matter and energy, following the same laws. Yet we have the capacity to step back, mentally, and consider the universe as a whole. We can contemplate cosmic horizons even though we cannot cross them. We can imagine regions we cannot observe. We can construct theories that extend beyond verification. This capacity for imagination and abstraction might be consciousness's greatest power. We're not limited to direct observation. We can reason beyond what we see. We can build mathematics and physics that describe realms we cannot access. The cosmic horizon limits observation, but not thought. We can think about infinity even if we cannot observe it. We can contemplate other universes even if we cannot visit them. This makes the cosmic horizon both a limit and an invitation. It marks the boundary of observation while opening the space for imagination. Science takes us to the boundary. Philosophy and mathematics take us beyond, into realms of possibility and abstraction. We cannot verify what lies beyond the horizon observationally, but we can explore it conceptually, constructing models and theories that might describe reality even where reality cannot be directly examined. The cosmic horizon teaches us something essential about existence itself. Not everything can be known. Not every question can be answered through observation. Some boundaries are absolute, set by the structure of reality rather than by human limitation. This is humbling. We like to think that given enough time and intelligence, everything can be understood. The cosmic horizon proves otherwise. There are regions of space we will never see, events we will never observe, phenomena we will never measure. The boundary is real and permanent, yet this limitation is also strangely comforting. It means the universe is larger than human comprehension. Reality exceeds what any mind can fully grasp. There will always be more to wonder about, more to contemplate, more mystery at the edges of knowledge. The horizon reminds us that wonder is appropriate. We stand on a small planet, looking outward at immense distances, seeing backward through vast stretches of time. What we observe is remarkable. That we can observe anything at all is remarkable. That we can understand what we observe well enough to recognize its limits is perhaps most remarkable of all. As this exploration concludes, we return to the essential facts. The universe has a boundary in observation, set by light speed and cosmic age. This boundary is called the cosmic horizon. Beyond it lie regions we cannot see, separated from us by insurmountable barriers of space and time. These regions probably contain more galaxies, more stars, more structure. The universe likely extends far beyond what we can observe, possibly infinitely. The cosmic horizon hides this vast expanse from view, not because nature is cruel or mysterious, but simply because information takes time to travel and the universe has a finite age. Understanding the cosmic horizon means accepting that some things remain unknown. The universe doesn't owe us complete knowledge. It exists on its own terms, following physical laws that create natural boundaries to observation and influence. The cosmic horizon is one such boundary. It divides the observable from the unobservable, the reachable from the unreachable, the knowable from the forever mysterious. This boundary will always exist. As long as light has a finite speed and the universe has a finite age, there will be regions we cannot see. As long as space continues expanding, there will be regions we can never reach. The cosmic horizon is permanent, an eternal limit to human knowledge about the cosmos, but within that limit lies vast space to explore, countless phenomena to study, mysteries enough to occupy intelligence for ages to come. The observable universe is enormous. It contains opportunities for discovery and understanding that will take civilizations millions or billions of years to fully exploit. The cosmic horizon defines the scope of possible exploration, while ensuring that exploration never truly ends. There's always more to learn about regions within the horizon. As technology improves and understanding deepens, new details emerge. The horizon limits the total scope, but not the depth of investigation within that scope. Perhaps this is the final lesson. Boundaries create meaning. If everything were accessible, nothing would be special. The cosmic horizon makes the observable universe precious, precisely because it's limited. What we can see and study represents a privileged sample, a window into structure and history that extends beyond our reach. We're fortunate to occupy this window at this moment in cosmic history. The universe is old enough for complexity to have emerged, and young enough for evidence to remain abundant. We can ask deep questions about cosmic origins and have realistic hope of finding answers. The cosmic horizon limits us, but it hasn't yet closed off so much that understanding becomes impossible. As we rest at this boundary between the known and the unknown, we can appreciate both what we've learned and what remains mysterious. The cosmic horizon is understood. Its nature, its causes, its evolution through time are all mapped by theory and confirmed by observation. We know why the boundary exists and what it represents, but beyond the boundary lies everything we cannot know. Vast regions of space, possibly infinite in extent, countless galaxies we will never see, perhaps other universes with different physics, maybe even forms of existence we cannot imagine. The cosmic horizon conceals all this, holding these mysteries beyond the reach of any possible observation. This combination of knowledge and mystery, understanding and wonder, defines our relationship with the cosmos. We've pushed our awareness to the absolute limits of what space and time permit. We've mapped the observable universe and understood the boundary that confines observation. We've achieved remarkable cosmic knowledge while recognizing its necessary limits. The cosmic horizon stands as a monument to both human achievement and human limitation. Achievement because we've understood something so profound and fundamental about cosmic structure. Limitation because we've recognized that understanding has boundaries we cannot cross. Sleep now with this knowledge. The universe extends beyond what can be seen. The cosmic horizon marks the edge of observation. Beyond it lies the eternal unknown, vast and mysterious and forever unreachable. Yet the horizon itself is known, understood, mapped. In that understanding lives a deep satisfaction, the pleasure of comprehending even what we cannot observe. The boundary we cannot cross is also the boundary we can understand. That understanding, that grasp of cosmic limits, represents the triumph of consciousness over the constraints of local existence. We're confined to one region of space, but our awareness extends to the very edges of what's possible. The cosmic horizon limits our observations, but not our comprehension. We understand the boundary even as we accept we cannot cross it. Rest with this knowledge. The cosmos is larger than human comprehension, but the boundaries of comprehension themselves can be understood. The cosmic horizon teaches us where observation ends and imagination begins, where verified knowledge yields to reasoned speculation, where the observable universe fades into the unreachable beyond. Before we conclude entirely, it's worth pausing to consider the extraordinary privilege of being able to contemplate cosmic horizons at all. For billions of years, the universe existed without conscious observers. Stars formed and died. Galaxies collided and merged. Space expanded. All of this occurred without anyone to witness or understand it. Then, on at least one planet, life emerged. Single cells became complex organisms. Nervous systems developed. Brains grew larger and more sophisticated. Eventually, consciousness arose, bringing with it the capacity for self-reflection and cosmic awareness. One species, among millions on one planet, developed the ability to ask questions about the universe itself. This species, humanity, has existed for only a tiny fraction of cosmic history. Anatomically, modern humans appeared perhaps 300,000 years ago. That's roughly 1/40,000th of the universe's current age. For most of human existence, we didn't know about galaxies, cosmic expansion, or the true scale of space and time. Only in the last century did we discover that the universe extends beyond our galaxy. Only in the last few decades did we map the cosmic microwave background and understand the early universe in detail. Only in the last few years have we observed gravitational waves and detected thousands of exoplanets. Our cosmic knowledge has exploded in an incredibly short time. This rapid expansion of understanding is remarkable. Within a human lifetime, our picture of the cosmos has transformed completely. People born when we thought the universe was static lived to see evidence for the Big Bang and accelerating expansion. Those who learned about 9 planets lived to see discoveries of thousands of worlds around other stars. Cosmology has progressed from speculation to precision science within living memory. The cosmic horizon represents the current limit of this expansion. We've pushed observation as far as physics permits. We've mapped the observable universe from the cosmic microwave background to the nearest galaxies. We understand the structure, history, and evolution of the cosmos to a remarkable degree. The horizon marks where this understanding necessarily pauses, where observation cannot advance further. Yet even reaching this limit represents achievement. We've gone from ignorance of galaxies to mapping cosmic structure across billions of light years. We've gone from wondering what stars are to understanding stellar evolution, nucleosynthesis, and supernova dynamics. We've gone from treating the universe as static to measuring its expansion and acceleration. Every step required ingenuity, careful observation, and theoretical insight. The cosmic horizon rewards this effort by revealing its nature. We understand why the horizon exists. We know how it evolves. We can predict what lies beyond based on extrapolation from what we observe. The boundary that limits observation is itself understood, characterized and incorporated into our cosmological theories. We've achieved knowledge of the limits of knowledge itself. This understanding is perhaps consciousness's highest achievement. Not just knowing particular facts, but knowing the boundaries of possible knowledge. Not just observing phenomena, but understanding the structure that permits or prevents observation. The cosmic horizon is more than a limit. It's a revealed limit, one we can study and characterize even though we cannot cross it. As conscious beings contemplating cosmic horizons, we participate in something profound. The universe examines itself through us. Matter organized into particular patterns gains the ability to reflect on cosmic structure. The atoms in our bodies came from stars. The energy powering our thoughts comes ultimately from the sun. We're not separate from the cosmos. We're part of it, temporarily configured in ways that permit awareness and understanding. This awareness is fleeting in cosmics terms. Individual humans live perhaps 100 years. Civilizations might last thousands or millions of years. Even if humanity survives billions of years, eventually the sun will die. Earth will become uninhabitable, and whatever survives will need to find new homes among the stars. Consciousness, wherever it exists, is temporary and fragile. Yet while it exists, consciousness illuminates the universe in a unique way. Galaxies shine whether or not anyone observes them. But when conscious beings observe galaxies and understand what they're seeing, something new enters the universe. Information becomes knowledge. Pattern becomes meaning. The cosmos becomes comprehensible, at least partially, at least from limited local perspectives. The cosmic horizon shapes this comprehension by defining its scope. We can comprehend our local region. We can infer what lies beyond. But our understanding is necessarily incomplete because most of the universe remains beyond observation. This incompleteness is not a failure. It's a feature of how consciousness works when embedded in an expanding universe with finite light speed and finite cosmic age. Perhaps in other regions of space separated from us by vast distances and cosmic horizons, other conscious beings contemplate their own cosmic horizons. They ask the same questions we do. They observe different regions of space while being unable to observe ours. They construct cosmological theories and reach similar conclusions about cosmic structure and evolution. Each consciousness, wherever it arises, finds itself surrounded by a horizon that limits but also defines the scope of possible understanding. In this way, cosmic horizons might be universal features of consciousness in the cosmos. Any observer, anywhere, in any era, finds themselves confined to a causal patch surrounded by regions beyond their observation. The details vary, different locations, different times, different observable regions, but the structure is the same. Consciousness is local, observation is limited, understanding is necessarily incomplete, yet consciousness persists in seeking understanding despite these limits. We ask questions knowing some cannot be answered. We build theories that extend beyond verification. We imagine what lies beyond cosmic horizons even though we cannot observe it. This drive to understand, to push against boundaries, to explore both physically and conceptually, might be consciousness's defining characteristic. The cosmic horizon thus becomes a symbol for the relationship between consciousness and cosmos. the boundary between known and unknown, between observed and inferred, between verified and imagined. Consciousness stands at this boundary, looking outward, asking questions, constructing theories, always aware of the limits, but never quite satisfied with them. This dissatisfaction drives science forward. If we accepted limits passively, we wouldn't have discovered galaxies, measured cosmic expansion, or detected the cosmic microwave background. Each discovery pushed understanding farther, revealing new phenomena and new questions. The cosmic horizon represents the current limit, but who knows what future observations and theories might reveal about regions currently beyond our reach. Perhaps future physics will find ways to extract more information from observations within the horizon. Perhaps theoretical advances will provide stronger constraints on what lies beyond. Perhaps new phenomena, gravitational waves, neutrino backgrounds, exotic particles, will carry information from regions currently inaccessible. The horizon might remain, but our understanding of what it conceals might deepen. Or perhaps the horizon is truly absolute, marking a permanent limit to observational knowledge. Even so, consciousness can contemplate the limit itself, can understand why it exists, can imagine what lies beyond. The boundary between known and unknown is also an invitation to thought, to speculation, to creative theorizing about possibilities that exceed direct verification. As we finally conclude this journey to the cosmic horizon, we can appreciate the privilege of being able to make this journey at all. We exist. We're conscious. We can observe the universe and understand what we observe well enough to recognize the limits of observation. This combination of existence, awareness, and understanding is rare in the cosmos and precious in its rarity. The cosmic horizon marks where understanding pauses. Beyond it lies mystery, vastness, and the unknown, but the boundary itself is understood. We know why it exists and what it represents. This knowledge, this grasp of cosmic limits, is the achievement of consciousness reaching outward as far as space and time permit, then recognizing the boundaries with clear-eyed understanding. Sleep well with this understanding. You've journeyed to the edge of the observable universe and contemplated what lies beyond. You've understood the cosmic horizon as well as anyone can. The mystery remains, the vastness continues, the unknown persists, but the boundary is known, the limit comprehended, the edge of observation mapped and characterized. Rest now at this boundary between known and unknown, between observed and inferred, between the universe we can study and the universe we can only imagine. The cosmic horizon surrounds you always, defining the limits of possible knowledge, while inviting endless contemplation of what might lie beyond. The boundary we cannot cross is also the boundary we can understand, and in that understanding lies a deep and abiding satisfaction.